Hello there, and welcome to the Sleepwalk Space. If you're someone who likes to unwind by thinking about planets, moons, and the gentle wonders of our solar system, you're in the right place. Tonight, we're going to explore our cosmic neighborhood, the familiar worlds that circle our sun, and the countless fascinating details that make each one unique. We'll visit ice giants and rocky deserts, moons with hidden oceans, and planets with winds that never stop. Some of what you'll hear might surprise you, but all of it is real. And if you enjoy these sleepy journeys, you're welcome to like and subscribe. It helps others find their way here too. But for now, get comfortable. Let your body rest. Let your thoughts wander, and let's begin. Mercury is the smallest planet in our solar system. It's tiny, just slightly larger than Earth's moon, and it moves through space with quiet precision. Despite its size, Mercury is a world of extremes. Its surface is covered in craters, ancient scars from billions of years of impacts. The planet has no atmosphere to speak of, just a thin veil of atoms blown off its surface by the solar wind. During the day, temperatures soar to over 800 degrees Fahrenheit, hot enough to melt lead. But at night, with no atmosphere to trap the heat, temperatures plummet to nearly 300 degrees below zero. It's a world of fire and ice, constantly shifting between brutal extremes. Yet despite this, Mercury endures, spinning slowly, completing 3 rotations for every 2 orbits around the Sun. It's a small world with a big story, quietly circling in the innermost lane of our solar system. Venus is the hottest planet in our solar system. Even though Mercury is closer to the Sun, Venus holds the record with the highest surface temperatures. The reason is its atmosphere, a thick blanket of carbon dioxide that traps heat in a runaway greenhouse effect. The surface temperature on Venus is around 900 degrees Fahrenheit, hot enough to melt zinc. The atmospheric pressure is crushing, about 90 times that of Earth, equivalent to being nearly a mile beneath the ocean. The air is filled with clouds of sulfuric acid, and the sky glows a dim orange. It's a harsh, hostile world, but it's also beautiful in its own way. From space, Venus shines brilliantly, the brightest planet in our sky, often called the morning or evening star. It rotates slowly, taking longer to spin once on its axis than it does to orbit the Sun. And it spins backwards compared to most planets, rolling in the opposite direction. Venus is a world of extremes, shrouded in mystery, glowing softly in the dark. Earth is the only planet known to support life. It's a blue marble suspended in space, covered with oceans, continents, and clouds. About 71% of Earth's surface is water, and that water is essential to everything we know. The atmosphere is a delicate mix of nitrogen and oxygen, just right for breathing, just right for protecting us from harmful radiation. Earth has seasons, driven by the tilt of its axis and a magnetic field that shields us from solar wind. It's the 3rd planet from the Sun, sitting in the habitable zone where temperatures allow liquid water to exist. From space, Earth looks peaceful, serene, a fragile oasis in the vastness. But beneath that calm surface, the planet is alive with motion. Tectonic plates shift, volcanoes erupt, and weather systems swirl across the globe. Earth is dynamic, ever-changing, and for now, it's the only home we've ever known. A small, quiet world where life found a way to flourish. Mars is often called the Red Planet. Its surface is covered in iron oxide, rust, which gives it that distinctive reddish hue. Mars is smaller than Earth, about half the diameter. and it has a thin atmosphere made mostly of carbon dioxide. The air is so thin that liquid water cannot exist on the surface. Instead, water is locked away in ice at the poles or hidden beneath the ground. Mars has the tallest volcano in the solar system, Olympus Mons, which stands nearly 13 miles high, almost 3 times the height of Mount Everest. It also has a massive canyon system, Valles Marineris, that stretches over 2,500 miles long and plunges up to 4 miles deep. The planet has seasons, polar ice caps, and dust storms that can engulf the entire planet. Days on Mars are just slightly longer than Earth days, about 24 hours and 37 minutes. And the sky, instead of blue, glows a soft butterscotch color during the day. Mars is cold, dry, and barren, but it holds clues to the past, hints of ancient rivers and lakes, and the possibility that life may have once existed there. Jupiter is the largest planet in our solar system. It's a gas giant, more than 11 times the diameter of Earth, and more massive than all the other planets combined. Jupiter has no solid surface, just layers of gas and liquid swirling in constant motion. Its atmosphere is made mostly of hydrogen and helium, with clouds of ammonia and water. The planet is famous for its Great Red Spot, a massive storm that has been raging for at least 400 years. The storm is so large that 3 Earths could fit inside it. Jupiter rotates incredibly fast, completing a full spin in just under 10 hours, which creates powerful winds and dynamic weather patterns. The planet has a strong magnetic field, the strongest of any planet in the solar system, and it's surrounded by dozens of moons. Jupiter acts as a kind of cosmic shield, its gravity pulling in comets and asteroids that might otherwise threaten the inner planets. It's a giant, a guardian, a swirling world of color and motion, quietly dominating the outer solar system. Saturn is known for its stunning rings. These rings are made of billions of pieces of ice and rock, some as small as grains of sand, others as large as mountains. They stretch out over 175,000 miles, but are incredibly thin, in some places only about 30 feet thick. Saturn itself is a gas giant, similar to Jupiter but slightly smaller. Its atmosphere is mostly hydrogen and helium, with clouds that form delicate bands of yellow and gold. Saturn is the least dense planet in the solar system. In fact, if you could find a bathtub big enough, Saturn would float. The planet has over 80 moons, including Titan, which is larger than Mercury and has a thick atmosphere and lakes of liquid methane. Saturn rotates quickly, with the day lasting just over 10 hours, and its winds can reach speeds of over 100 miles per hour. The rings may be temporary, possibly only a few 100 million years old, and they may eventually disappear as the ice and rock slowly spiral into the planet. Saturn is elegant, serene, a jewel of the solar system, quietly spinning in the distant dark. Uranus rotates on its side. While most planets spin like tops, Uranus rolls like a ball, its axis tilted at about 98 degrees. This means that for part of its orbit, one pole points almost directly at the sun, while the other is in darkness. Seasons on Uranus last for decades, and each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Uranus is an ice giant, made mostly of water, methane, and ammonia ices surrounding a small rocky core. Its atmosphere is a pale blue color, tinted by methane, and it's remarkably calm compared to the other gas giants. Uranus has faint rings, much darker and thinner than Saturn's, and at least 27 known moons. The planet is so far from the sun that it takes 84 Earth years to complete a single orbit. Temperatures in its atmosphere drop to around minus 370 degrees Fahrenheit, making it one of the coldest planets in the solar system. Uranus is quiet, distant, and strange, a world turned on its side, drifting slowly through the outer reaches of our solar system. Neptune is the windiest planet in our solar system. Even though it's far from the Sun and receives very little energy, Neptune has the fastest winds ever recorded on any planet, reaching speeds of over 200 miles per hour. These supersonic winds whip through the planet's atmosphere, creating massive storms and dark spots that come and go over time. Neptune is similar to Uranus in composition, an ice giant made of water, methane, and ammonia. Its deep blue color comes from methane in the atmosphere, which absorbs red light and reflects blue. Neptune has 14 known moons, the largest of which is Triton, a strange icy world that orbits in the opposite direction of Neptune's rotation. Triton is one of the coldest objects in the solar system, with geysers that spew nitrogen gas into space. Neptune takes 165 Earth years to orbit the Sun, meaning it has only completed one full orbit since it was discovered in 1846. It's a dark, distant world, lit only faintly by the faraway Sun, swirling with motion, energy, and wind. Pluto is no longer considered a planet. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet, sparking debate and nostalgia around the world. Pluto is small, smaller than Earth's moon, and it orbits in the distant Kuiper Belt, a region filled with icy bodies beyond Neptune. Its surface is a mix of frozen nitrogen, methane, and carbon monoxide, with mountains made of water ice as hard as rock. Pluto has a thin atmosphere that freezes and falls to the surface as snow when the planet moves farther from the Sun. It has 5 known moons, the largest being Charon, which is so big that Pluto and Charon are sometimes considered a double system. They orbit a common point in space between them. Pluto's orbit is elliptical and tilted, taking 248 Earth years to complete. When the New Horizons spacecraft flew by in 2015, it revealed a world far more complex and beautiful than anyone expected, with plains, valleys, and a heart-shaped region of smooth ice. Pluto may not be a planet anymore, but it's still a world, cold, distant, and quietly remarkable. The Sun is a star at the center of our solar system. It's a massive ball of hot plasma, held together by gravity and powered by nuclear fusion in its core. The Sun contains about 99.86% of the total mass of the solar system. Everything else, all the planets, moons, asteroids, and comets, makes up less than 0.14%. The Sun's core reaches temperatures of around 27 million degrees Fahrenheit, where hydrogen atoms fuse into helium, releasing energy in the form of light and heat. That energy takes thousands of years to reach the surface, and then just 8 minutes to travel to Earth. The Sun is about 4.6 billion years old, roughly halfway through its life. In another 5 billion years, it will expand into a red giant, engulfing the inner planets before cooling into a white dwarf. The Sun rotates, but not as a solid object. Its equator spins faster than its poles, completing a rotation in about 25 days. The Sun is the reason we exist, the source of light, warmth, and energy, quietly burning in the center of our cosmic neighborhood. Mercury has no moons. Unlike most planets, Mercury orbits the Sun alone, with no natural satellites. Its proximity to the Sun and its small size make it difficult for a moon to form or remain stable. any object that might have once orbited Mercury would likely have been pulled away by the sun's gravity or crashed into the planet's surface. Mercury's solitude is part of what makes it unique. A small, lonely world racing around the sun at incredible speeds. It moves faster than any other planet, completing an orbit in just 88 Earth days. The name Mercury comes from the Roman messenger god, fitting for the planet's swift motion. Without a moon, Mercury has no tides, no companion in the sky, just the sun, growing larger and smaller as the planet follows its elliptical path. It's a quiet existence, spinning slowly through the inner solar system, marked only by craters and the distant stars. Venus rotates backwards compared to most planets. While most planets spin counterclockwise when viewed from above the sun's north pole, Venus spins clockwise. This retrograde rotation means that on Venus, the sun rises in the west and sets in the east. Scientists aren't entirely sure why Venus rotates this way. It may have been knocked off course by a massive collision early in its history, or its thick atmosphere may have influenced its rotation over billions of years. Whatever the cause, the result is a slow, backwards spin. A single day on Venus, one full rotation takes 243 Earth days, longer than its year, which is 225 Earth days. And this means a day on Venus is longer than its year, a strange and beautiful quirk of planetary motion. Time moves differently there, stretched and reversed, as the planet turns slowly beneath its heavy clouds. Earth has one moon and is relatively large. The moon is about 1/4 the size of Earth, making it the 5th largest moon in the solar system. It's thought to have formed about 4.5 billion years ago when a Mars-sized object collided with the early Earth, sending debris into orbit that eventually coalesced into the moon. The moon's gravity affects Earth in profound ways. It creates tides in the oceans, pulling the water toward it as it orbits. The moon also stabilizes Earth's axial tilt, which helps regulate our climate and seasons. Without the moon, Earth's tilt could vary wildly, leading to extreme climate shifts. The moon is tidally locked to Earth, meaning the same side always faces us. We never see the far side from Earth, though spacecraft have photographed it. The moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. Billions of years from now, it will be much farther away, and Earth's days will be longer. For now, the moon hangs in our sky, a constant companion, glowing softly through the night. Mars has 2 small moons, Phobos and Deimos. They're both irregularly shaped and covered in craters, more like captured asteroids than traditional moons. Phobos is the larger of the two, about 14 miles across, and it orbits very close to Mars, completing a full orbit in just over 7 hours. It's so close that it's slowly spiraling inward, and in about 50 million years, it will either crash into Mars or break apart into a ring. Deimos is smaller, about 7.5 miles across, and it orbits farther out, taking about 30 hours to complete an orbit. Both moons are named after the sons of Ares, the Greek god of war, with Phobos meaning fear and Deimos meaning dread. From the surface of Mars, Phobos would appear to rise and set twice a day, moving quickly across the sky. Deimos, on the other hand, would hang in the sky for days, barely moving. These tiny moons are remnants of the early solar system, captured by Mars's gravity, circling quietly above the red plains below. Jupiter has at least 95 known moons. It's a miniature solar system of its own, with moons of all shapes and sizes orbiting the gas giant. The 4 largest moons, discovered by Galileo in 1610, are called the Galilean moons: Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system, with plumes of sulfur and lava erupting constantly from its surface. Europa is covered in a thick shell of ice, beneath which lies a vast ocean of liquid water, making it one of the most promising places to search for life. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury, and it's the only moon known to have its own magnetic field. Callisto is heavily cratered, one of the oldest surfaces in the solar system, quiet and ancient. Beyond these four, Jupiter has dozens of smaller moons, some only a few miles across. Some orbit in the same direction as Jupiter's rotation, while others move in retrograde, likely captured objects from the outer solar system. Together, they form a dynamic, complex system, a family of worlds circling the king of planets. Saturn has over 80 known moons. Like Jupiter, Saturn's moons vary widely in size and character. The largest is Titan, a world larger than Mercury, with a thick nitrogen atmosphere and lakes of liquid methane and ethane on its surface. Titan is one of the most Earth-like places in the solar system, with weather, seasons, and a dynamic surface shaped by wind and rain, though the rain is methane, not water. Enceladus is another fascinating moon, small and icy, with geysers erupting from cracks near its south pole. These geysers shoot water vapor and ice particles into space, suggesting a subsurface ocean beneath the ice. Other notable moons include Mimas, which has a massive crater that makes it resemble the Death Star, and Iapetus, which has one bright hemisphere and one dark hemisphere, giving it a two-toned appearance. Saturn's moons are diverse, strange, and beautiful, each one a small world with its own story, quietly orbiting the ringed giant. Uranus has 27 known moons. Unlike most moons in the solar system, which are named after figures from Greek and Roman mythology, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. The largest moons are Titania, Oberon, Umbrio, Ariel, and Miranda. Miranda is particularly interesting, with a surface that looks like it was shattered and reassembled, featuring cliffs over 12 miles high, the tallest in the solar system. The moons of Uranus are icy and dark, reflecting very little light. They orbit in the same plane as Uranus's equator, which means they also orbit at a steep tilt relative to the Sun. This creates unusual seasonal patterns, with each moon experiencing long periods of sunlight and darkness as Uranus moves through its 84-year orbit. These moons are quiet, distant, and cold, circling a planet that itself is turned on its side, drifting through the outer solar system. Neptune has 14 known moons. The largest and most interesting is Triton, a strange, icy world with a retrograde orbit, meaning it moves in the opposite direction of Neptune's rotation. This suggests that Triton was not formed alongside Neptune, but was captured from the Kuiper Belt. Triton is one of the coldest places in the solar system, with surface temperatures around minus 390 degrees Fahrenheit. Despite the cold, Triton is geologically active, with geysers that erupt nitrogen gas and dark material into the thin atmosphere. These geysers create dark streaks on the surface, visible in images taken by Voyager 2. Triton's retrograde orbit is slowly decaying, and in a few billion years it will either crash into Neptune or be torn apart by tidal forces, possibly forming a ring around the planet. Neptune's other moons are much smaller, and many orbit in irregular, eccentric paths. Triton stands out, a captured world, cold and active, circling Neptune in defiance of the usual rules. The asteroid belt lies between Mars and Jupiter. It's a region filled with rocky debris, remnants from the early solar system that never coalesced into a planet. The asteroid belt contains millions of objects, ranging from tiny grains to bodies hundreds of miles across. The largest object in the belt is Ceres, a dwarf planet about 590 miles in diameter. Ceres is round with a rocky core and an icy mantle, and it may even have a subsurface ocean. Despite the name asteroid belt, the region is mostly empty space. The asteroids are spread out over a vast area, and spacecraft can pass through without much risk of collision. The belt is a reminder of the chaotic early days of the solar system, when planets were forming and collisions were common. Some asteroids are made of metal, likely the cores of larger bodies that were shattered by impacts. Others are carbonaceous, rich in organic compounds. The asteroid belt is a quiet graveyard of planetary building blocks, drifting slowly in the space between the inner and outer planets. The Kuiper belt is a region beyond Neptune. It's similar to the asteroid belt but much larger and more distant, stretching from about 30 to 55 astronomical units from the Sun. The Kuiper belt is home to icy bodies, remnants from the formation of the solar system. Pluto is the most famous resident, but there are many others, including Haumea, Makemake, and Eris. These objects are made mostly of frozen methane, ammonia, and water. They're cold, distant, and dark, receiving very little sunlight. The Kuiper belt is also the source of short-period comets, icy bodies that are occasionally nudged by gravity into orbits that bring them closer to the Sun. As they approach, the ice begins to vaporize, creating the glowing tails we see from Earth. The Kuiper belt is a frontier, a distant region we're only beginning to explore, filled with ancient, frozen worlds that hold clues to the origins of our solar system. Comets are icy visitors from the outer solar system. They're made of frozen water, carbon dioxide, methane, and ammonia, mixed with dust and rock. When a comet's orbit brings it close to the Sun, the ice begins to vaporize, creating a glowing coma around the nucleus and a long tail that can stretch for millions of miles. The tail always points away from the Sun, pushed by the solar wind and radiation pressure. Comets can have two tails, one made of gas and one made of dust, each glowing in different ways. Some comets have very long elliptical orbits, taking hundreds or even thousands of years to complete. Others, like Halley's Comet, return more frequently, passing by Earth every 75 to 76 years. Comets are ancient, pristine objects, largely unchanged since the solar system formed. They carry with them the chemistry of the early solar system, and studying them helps us understand where we came from. They're beautiful, transient visitors, glowing softly as they pass through the inner solar system before returning to the dark. Meteoroids are small pieces of rock or metal in space. When they enter Earth's atmosphere, they're called meteors, and they create bright streaks of light as they burn up from friction with the air. Most meteors are no larger than a grain of sand, but they can produce brilliant flashes as they streak across the sky. If a meteoroid survives the journey through the atmosphere and lands on Earth's surface, it's called a meteorite. Meteorites can be made of stone, metal, or a mixture of both, and they provide valuable information about the composition of asteroids and the early solar system. Some meteorites are fragments from Mars or the Moon. ejected by impacts and eventually captured by Earth's gravity. Meteor showers occur when Earth passes through the debris left behind by a comet, and dozens or even hundreds of meteors can be seen in a single night. They're fleeting, beautiful moments, reminders of the constant motion and interaction of objects in space. The planets move in elliptical orbits around the Sun. While we often think of orbits as perfect circles, they're actually ellipses, stretched circles with the Sun at one of the two foci. The shape of an orbit is described by its eccentricity, a measure of how elongated it is. A perfect circle has an eccentricity of 0, while a more stretched orbit has a higher eccentricity. Earth's orbit is nearly circular, with an eccentricity of about 0.07. But other planets have more eccentric orbits. Mercury, for example, has an eccentricity of about 0.21, meaning its distance from the Sun varies significantly throughout its orbit. This affects the amount of sunlight it receives and contributes to the planet's extreme temperature variations. The planets also orbit at different speeds, with those closer to the Sun moving faster than those farther out. Mercury races around the Sun in just 88 days, while Neptune takes 165 years. These elliptical paths, governed by gravity and motion, create the beautiful, predictable dance of the planets. Each planet has a unique axial tilt. The axial tilt is the angle between a planet's rotational axis and its orbital plane, and it determines how much the planet experiences seasons. Earth has an axial tilt of about 23.5 degrees, which gives us our familiar cycle of spring, summer, autumn, and winter. Mars has a similar tilt, about 25 degrees, so it also experiences seasons, though they're longer because Mars takes longer to orbit the Sun. Uranus, with its extreme tilt of 98 degrees, has the most unusual seasons, with each pole experiencing 42 years of continuous daylight followed by 42 years of darkness. Jupiter and Venus have very small axial tilts, less than 3 degrees, so they don't experience significant seasonal changes. The axial tilt of a planet affects not just its seasons, but also its climate, wind patterns, and even the possibility of life. It's one of the many factors that makes each planet unique, contributing to the diversity of worlds in our solar system. Planets emit radio waves. While we can't hear them with our ears, planets produce radio emissions that can be detected by specialized instruments. Jupiter, for example, is a powerful source of radio waves generated by charged particles moving through its strong magnetic field. These radio emissions can be picked up by radio telescopes on Earth, and they sound like static or whistles when converted into audio. Saturn, Uranus, and Neptune also emit radio waves, each with its own characteristic signature. Even Earth produces radio emissions, both natural and artificial. Studying these radio waves helps scientists understand the magnetic fields, atmospheres, and internal structures of planets. It's another way of listening to the solar system, tuning in to the invisible signals that planets send out into space. The cosmos is not silent. It hums with energy, motion, and radiation, a symphony of waves traveling through the dark. The gravity of each planet is different. Gravity depends on a planet's mass and size, and it determines how much an object weighs on that planet's surface. On Earth, we're used to a certain level of gravity, defined as 1g. On the Moon, gravity is only about 1/6 of Earth's, so you'd weigh much less and could jump much higher. On Mars, gravity is about 38% of Earth's, still lower but closer to what we're used to. On Jupiter, if it had a solid surface, gravity would be about 2.5 times that of Earth, meaning you'd feel much heavier, and movement would be much more difficult. On smaller bodies like asteroids or comets, gravity is so weak that you could jump off the surface entirely, drifting away into space. Gravity shapes the way planets hold on to their atmospheres, the way moons orbit, and the way objects move across their surfaces. It's a fundamental force, invisible but ever present, pulling everything toward the center of mass. The atmospheres of planets vary greatly. Earth's atmosphere is a mix of nitrogen, oxygen, and trace gases, stable and breathable for life as we know it. Venus has a thick atmosphere of carbon dioxide with clouds of sulfuric acid, creating a runaway greenhouse effect and crushing surface pressure. Mars has a thin atmosphere, mostly carbon dioxide, with very low pressure, making it inhospitable to liquid water on the surface. Jupiter, Saturn, Uranus, and Neptune have a thick atmospheres of hydrogen and helium, with clouds of ammonia, methane, and water at different levels. These gas giants have no solid surface, just layers of gas that gradually become denser and hotter as you descend. Mercury has almost no atmosphere, just a thin exosphere of atoms, knocked off the surface by the solar wind. The diversity of atmospheres reflects the different conditions, distances from the Sun, and histories of each planet. Atmospheres protect, they trap heat, they create weather, and they shape the worlds we see. Days and years are different on each planet. A day is the time it takes for a planet to complete one full rotation on its axis, while a year is the time it takes to orbit the Sun. On Earth, a day is 24 hours and a year is 365 days. On Mercury, a day lasts 59 Earth days, but a year is only 88 Earth days, so a single day on Mercury is about 2/3 of its year. On Venus, as we've mentioned, a day is 243 Earth days, longer than its year of 225 Earth days. On Mars, a day is just slightly longer than Earth's, about 24 hours and 37 minutes, but a year is 687 Earth days, almost twice as long. On Jupiter, a day is less than 10 hours, but a year is nearly 12 Earth years. The gas giants spin quickly but orbit slowly, while the rocky planets closer to the Sun have a wide range of day and year lengths. These differences affect everything, from weather patterns to the way time is experienced on each world. Planets have different colors when viewed from space. Mercury appears gray and brownish, its surface covered in ancient dark rock. Venus is a bright yellowish white, its thick clouds reflecting sunlight brilliantly. Earth is the famous blue marble, with white clouds, green and brown land masses, and deep blue oceans. Mars is distinctly red, its surface rich in iron oxide. Jupiter is a swirl of browns, whites, and reds with bands of clouds and the great red spot standing out. Saturn is a pale yellow, softer and more muted than Jupiter. Uranus and Neptune are both shades of blue. Uranus a pale cyan, and Neptune a deeper, richer blue, both colored by methane in their atmospheres. Each planet's color tells a story about its composition, its atmosphere, and the way it interacts with sunlight. From a distance, these colors make each planet recognizable, a unique signature in the vastness of space. The temperature on planets varies wildly. Mercury, despite being closest to the Sun, is not the hottest planet. It has extreme temperature swings from over 800 degrees Fahrenheit during the day to minus 290 degrees at night. Venus is the hottest planet, with surface temperatures around 900 degrees Fahrenheit, thanks to its thick atmosphere trapping heat. Earth has a moderate range. with average temperatures around 59 degrees Fahrenheit, but varying widely depending on location and season. Mars is cold, with average temperatures around minus 80 degrees Fahrenheit, though it can get warmer at the equator during the day. Jupiter, Saturn, Uranus, and Neptune are all extremely cold, with temperatures dropping to hundreds of degrees below zero in their upper atmospheres. The farther from the Sun, the colder it gets, but atmospheric composition and internal heat also play a role. Temperature affects the state of matter, the possibility of life, and the behavior of weather on each planet. Some planets have magnetic fields, and some do not. Earth has a strong magnetic field, generated by the motion of molten iron in its core. This field protects us from the solar wind and cosmic radiation, creating the magnetosphere that shields the atmosphere. Mercury also has a magnetic field, though it's much weaker than Earth's. Venus and Mars do not have global magnetic fields, which is one reason their atmospheres are thinner and more vulnerable to erosion by the solar wind. Jupiter has the strongest magnetic field of any planet, generated by metallic hydrogen in its interior. Saturn, Uranus, and Neptune also have magnetic fields, though they're structured differently and may be generated by different mechanisms. A planet's magnetic field affects its ability to retain an atmosphere, the presence of auroras, and the way it interacts with charged particles from the Sun. It's an invisible shield, a protective bubble around some worlds, absent on others. Auroras occur on several planets. On Earth, auroras are caused by charged particles from the solar wind colliding with atoms in the atmosphere, creating beautiful displays of light near the poles. But Earth is not the only planet with auroras. Jupiter and Saturn both have powerful auroras, much larger and more intense than Earth's, driven by their strong magnetic fields and interactions with the solar wind and their moons. Uranus and Neptune also have auroras, though they're less well studied. Even Mars, which lacks a global magnetic field, has localized auroras where ancient magnetic fields remain in the crust. These auroras are different from Earth's, more patchy and irregular, but they still create glowing displays in the Martian atmosphere. Auroras are a reminder of the dynamic relationship between planets and the Sun, a visible manifestation of invisible forces at work. Planetary rings are not unique to Saturn. While Saturn's rings are the most famous and spectacular, other planets also have rings. Jupiter has faint, narrow rings made of dust, likely from micrometeorite impacts on its inner moons. Uranus has a system of thin, dark rings, discovered in 1977 when the planet passed in front of a star, and the rings briefly blocked its light. Neptune also has rings, though they're faint and clumpy, with some sections brighter than others. These rings are made of ice and rock particles, ranging in size from tiny grains to larger chunks. Saturn's rings are by far the most extensive and beautiful, but the presence of rings on other planets shows that they can form in different ways and under different conditions. Rings are dynamic, constantly changing as particles collide, clump together, or drift away. They're a fleeting feature in planetary terms, existing for a while before eventually fading. The Great Red Spot on Jupiter is a massive storm. It's been raging for at least 400 years, possibly much longer, and it's so large that 2 or 3 Earths could fit inside it. The storm is an anticyclone, a high-pressure system that rotates counterclockwise in Jupiter's southern hemisphere. Winds at the edge of the storm reach speeds of over 400 miles per hour. The Great Red Spot has been shrinking over the past century, and scientists aren't sure why. It used to be much larger, but now it's about half the size it was in the late 1800s. Despite the shrinking, the storm remains powerful and shows no signs of dissipating. The red color may come from complex organic molecules or sulfur compounds in the atmosphere, but the exact cause is still uncertain. The Great Red Spot is a reminder of the dynamic, ever-changing nature of planetary atmospheres, a storm that has outlasted civilizations on Earth, still swirling in the clouds of a distant world. Saturn's rings may be relatively young. For a long time, scientists thought Saturn's rings were as old as the planet itself, formed billions of years ago from the debris of the early solar system. But recent data from the Cassini spacecraft suggests the rings may be much younger, possibly only a few 100 million years old. The rings are bright and icy, which suggests they haven't been exposed to space dust and debris for very long. If they were ancient, they would likely be darker and dirtier. The rings may have formed from the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Over time, the rings will continue to change, spreading out and fading, and eventually they may disappear entirely. Saturn's rings are beautiful, iconic, but they may also be temporary, a brief adornment in the life of the planet. Jupiter's moon Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by volcanic eruptions, with plumes of sulfur and sulfur dioxide shooting hundreds of miles into space. The volcanic activity is driven by tidal heating, the same force that keeps Europa's ocean liquid. Io is caught in a gravitational tug-of-war between Jupiter and the other Galilean moons, and this constant flexing generates immense heat inside the moon. The surface of Io is covered in volcanoes, lava flows, and calderas, with colors ranging from yellow and orange to red and black, created by sulfur and sulfur compounds. There are no impact craters on Io, because the surface is constantly being covered by new lava. Io is a world of fire, a small moon in constant turmoil, glowing faintly in the darkness of Jupiter's orbit. Europa may have an ocean beneath its ice. The surface of Europa is smooth and crisscrossed with cracks, suggesting that the ice shell is floating on a layer of liquid water beneath. This ocean could be tens of miles deep, containing more water than all of Earth's oceans combined. The ice shell is estimated to be 10 to 15 miles thick, but in some places it may be thinner, with areas where water may occasionally break through to the surface. Europa's ocean is kept liquid by tidal heating, the same process that drives Io's volcanoes. The gravitational pull of Jupiter and the other Galilean moons causes Europa to flex and bend, generating heat in its interior. If there's liquid water and heat, there's the possibility of life, perhaps simple microbes living in the dark, warm ocean beneath the ice. Europa is one of the most promising places in the solar system to search for life. A small, icy moon with a hidden sea, quietly orbiting Jupiter. Ganymede is the largest moon in the solar system. It's even larger than the planet Mercury, with a diameter of about 3,270 miles. Ganymede is unique among moons because it has its own magnetic field, the only moon known to have one. This suggests that it has a liquid iron core, similar to Earth. Ganymede's surface is a mix of two types of terrain: dark, heavily cratered regions that are billions of years old, and lighter, grooved areas that are younger and have been reshaped by tectonic activity. Beneath the surface, there may be a subsurface ocean similar to Europa, sandwiched between layers of ice. Ganymede's magnetic field creates auroras near its poles, glowing displays of light caused by charged particles interacting with the thin atmosphere. Ganymede is a complex, layered world, the largest moon in a solar system full of moons, quietly circling Jupiter. Callisto is one of the oldest surfaces in the solar system. Its surface is heavily cratered, scarred by billions of years of impacts, and it shows very little sign of geological activity. Unlike Io, Europa, and Ganymede, Callisto is quiet and stable, a relic from the early solar system. The surface is a mix of ice and rock, dark and ancient, with some of the oldest features we've seen anywhere. Callisto may also have a subsurface ocean deep beneath the ice, but if it exists, it's isolated and inactive. Callisto orbits farther from Jupiter than the other Galilean moons, so it experiences less tidal heating and less gravitational interaction. It's a peaceful, silent world, drifting through space, unchanged for eons, a frozen snapshot of the solar system's youth. Titan is the only moon with a thick atmosphere. It's larger than Mercury, and its atmosphere is even thicker than Earth's, made mostly of nitrogen with traces of methane and other hydrocarbons. The surface pressure on Titan is about 1.5 times that of Earth, and the atmosphere creates a thick orange haze that obscures the surface. Beneath the haze, Titan has lakes and seas of liquid methane and ethane, the only other place in the solar system besides Earth with stable liquid. On its surface, the temperature on Titan is extremely cold, around minus 290 degrees Fahrenheit, but the chemistry is complex and dynamic. Methane rain falls from the sky, carving rivers and shaping the landscape. There are sand dunes made of hydrocarbon particles, mountains made of water ice, and possibly cryovolcanoes that erupt with water and ammonia. Titan is one of the most Earth-like places in the solar system, not in temperature or composition, but in the presence of weather, erosion, and a dynamic surface. It's a strange, hazy world, rich with organic chemistry, quietly orbiting Saturn. Enceladus has geysers erupting from its south pole. This small, icy moon is one of the most geologically active bodies in the solar system. The geysers shoot water vapor and ice particles hundreds of miles into space, and some of this material falls back to the surface as snow, while the rest escapes and forms one of Saturn's faint outer rings. The geysers suggest that there is a subsurface ocean beneath the ice, warmed by tidal heating from Saturn's gravity. The water from the geysers contains salts and organic molecules, hinting at complex chemistry and the possibility of life. Enceladus is small, only about 300 miles across, but it's active and intriguing. The geysers are visible in images taken by the Cassini spacecraft, plumes of ice glowing in the sunlight as they erupt from cracks in the surface. Enceladus is a little moon with a big secret, a hidden ocean erupting into space. Triton is the only large moon with a retrograde orbit. It orbits Neptune in the opposite direction of the planet's rotation, which strongly suggests it was not formed alongside Neptune, but was captured from the Kuiper Belt. Triton is geologically active, with a young surface and geysers that erupt nitrogen gas, creating dark streaks on the icy plains. The temperature on Triton is around minus 390 degrees Fahrenheit, making it one of the coldest objects in the solar system. But despite the cold, the interior is active. Triton's retrograde orbit is unstable, and over billions of years, it's slowly spiraling inward. Eventually, it will get too close to Neptune and will be torn apart by tidal forces, possibly forming a spectacular ring system around the planet. Triton is a captured world, active and doomed, slowly falling toward its fate. Charon is so large relative to Pluto that they form a binary system. Charon is about half the size of Pluto, and instead of Charon orbiting around Pluto's center, both bodies orbit around a common point in space between them. This point, called the barycenter, lies outside of Pluto, which is unusual for a planet and moon system. Pluto and Charon are tidally locked to each other, meaning the same sides always face each other. From Pluto's surface, Charon would appear to hang in the same spot in the sky, never rising or setting. Charon's surface is gray and icy, with fewer features than Pluto, and it may have had a subsurface ocean in the past, though it's likely frozen now. The Pluto-Charon system is a unique pairing, two worlds locked in a gravitational dance, drifting together through the distant Kuiper Belt. Some asteroids have their own moons. These are called binary asteroids, and they're more common than you might think. The asteroid Ida, for example, has a small moon named Dactyl, only about a mile across. Other asteroids have 2 or even more moons, orbiting around them like miniature planetary systems. These moons likely formed from debris created by impacts or from material that was loosely bound to the asteroid. Studying binary asteroids helps scientists understand the formation and evolution of the solar system. Some asteroids are actually contact binaries, two objects that are touching each other, slowly orbiting their common center of mass. These systems are fragile and dynamic, shaped by collisions, gravity, and the slow passage of time. Even among asteroids, there's complexity and motion. Small worlds with smaller companions, drifting through space together. Ceres has bright spots on its surface. When the Dawn spacecraft arrived at Ceres in 2015, it discovered mysterious bright spots in a crater called a crater. These bright areas are made of salts, likely left behind by briny water that seeped up from beneath the surface and evaporated. Ceres may have a subsurface ocean or pockets of liquid water, kept warm by residual heat from its formation or from radioactive decay in its core. The bright spots are some of the most reflective features on Ceres, standing out against the dark, cratered surface. Ceres is classified as a dwarf planet and the largest object in the asteroid belt. It's round, differentiated, with a rocky core and an icy mantle. It's a small world with hints of activity, quietly orbiting between Mars and Jupiter, covered in ancient ice and salt. Some meteorites contain organic molecules. These carbon-based compounds are the building blocks of life, and finding them in meteorites suggests that the ingredients for life may be common throughout the solar system. The Murchison meteorite, which fell in Australia in 1969, contains amino acids, the building blocks of proteins, as well as other complex organic molecules. These molecules formed in space, in the cold, dark regions of the early solar system, and they were delivered to Earth by meteorites. This raises the possibility that life on Earth may have been seeded by material from space, or at least that the chemistry needed for life was already present before Earth fully formed. Meteorites are time capsules, carrying with them the chemistry of the early solar system, and they remind us that the universe is full of the ingredients for life, scattered throughout the stars. The sun goes through an 11-year cycle. This cycle is marked by changes in solar activity, including the number of sunspots, solar flares, and coronal mass ejections. At solar maximum, the Sun is very active, with many sunspots and frequent eruptions. At solar minimum, activity is much lower, with fewer sunspots and calmer conditions. The cycle is driven by the Sun's magnetic field, which flips every 11 years, with the north and south magnetic poles switching places. Solar activity affects space weather, which can impact satellites, communications, and even power grids on Earth. During solar maximum, auroras are more frequent and can be seen at lower latitudes. The Sun is not a static, unchanging ball of light. It breathes, it cycles, it pulses with activity, and it affects everything in the solar system. Solar flares are sudden bursts of energy from the Sun. They release vast amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Solar flares are caused by the sudden release of magnetic energy stored in the Sun's atmosphere. They can last from minutes to hours, and they're often accompanied by coronal mass ejections, which are huge clouds of charged particles that are hurled into space. When these particles reach Earth, they can cause geomagnetic storms, disrupt communications, and create beautiful auroras. Solar flares are powerful, dramatic events, a reminder that the Sun is a dynamic, active star. We live in the atmosphere of a star, bathed in its light and energy, and occasionally we're reminded of its power. The solar wind is a stream of charged particles from the Sun. It flows outward in all directions, carrying with it the Sun's magnetic field and creating a bubble around the solar system called the heliosphere. The solar wind interacts with the magnetic fields of planets, creating auroras and shaping magnetospheres. On planets without magnetic fields like Mars and Venus, the solar wind can strip away the atmosphere over time, eroding it particle by particle. The solar wind varies in strength and speed, depending on the Sun's activity. During solar storms, the wind can become much faster and denser, creating disturbances in space weather. The solar wind is invisible, but it's always there, flowing past the planets, shaping the environment of space, carrying the influence of the Sun to the farthest reaches of the solar system. The heliosphere extends far beyond the planets. It's the region of space dominated by the Sun's influence, where the solar wind and the Sun's magnetic field are stronger than the interstellar medium. The boundary of the heliosphere is called the heliopause, and it's located about 11 billion miles from the Sun, more than 3 times the distance from the Sun to Neptune. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Beyond the heliopause, the solar wind can no longer push back against the pressure of interstellar space, and the environment changes. The heliosphere is like a protective bubble, shielding the planets from some of the high-energy cosmic rays that fill the galaxy. It's vast, extending far beyond what we typically think of as the solar system, a bubble of the Sun's influence in the vastness of space. The Oort cloud is a distant shell of icy objects. It's thought to surround the solar system at a distance of about 2,000 to 100,000 astronomical units from the Sun, far beyond the Kuiper Belt. The Oort cloud is hypothetical, meaning we haven't observed it directly, but we infer its existence from the orbits of long-period comets. These comets have orbits that take them far beyond the planets, and they likely originate in the Oort cloud. The cloud is thought to contain trillions of icy bodies. remnants from the formation of the solar system, scattered to the outer reaches by the gravity of the giant planets. The Oort cloud is the most distant part of the solar system, a vast, diffuse shell of icy debris, barely held by the Sun's gravity, marking the boundary between the Sun's domain and the space between the stars. Spacecraft have visited every planet in the solar system. The first missions began in the 1960s, with flybys of Venus and Mars. In the decades since, we've sent spacecraft to every planet, from Mercury to Neptune, and even to dwarf planets like Pluto and Ceres. Mariner 10 flew by Mercury in the 1970s, and more recently, Messenger orbited the planet, mapping its surface in detail. Venus has been visited by dozens of missions, including landers that survived the harsh conditions for a short time before being destroyed by the heat and pressure. Mars has been explored by orbiters, landers, and rovers, with ongoing missions searching for signs of past or present life. The outer planets have been visited by Pioneer, Voyager, Galileo, Cassini, and Juno, each revealing new details about these giant worlds and their moons. New Horizons flew by Pluto in 2015, giving us our first close-up look at this distant dwarf planet. These missions have transformed our understanding of the solar system, turning distant points of light into real, complex worlds. The Voyager spacecraft are still sending data. Launched in 1977, Voyager 1 and Voyager 2 were designed to explore the outer planets. They flew by Jupiter and Saturn, with Voyager 2 continuing on to Uranus and Neptune. After completing their planetary missions, both spacecraft continued outward, heading toward interstellar space. Voyager 1 is now the most distant human-made object, over 14 billion miles from Earth, and it crossed into interstellar space in 2012. Voyager 2 is also in interstellar space, having crossed the heliopause in 2018. Both spacecraft are still operational, sending back data about the environment beyond the heliosphere. Their power sources are slowly declining, and eventually they will go silent. But for now, they continue to send faint signals across the vast distance, messages from the edge of the solar system, traveling through the dark. Mars rovers have explored the surface for years. The first successful rover, Sojourner, landed on Mars in 1997 and operated for about 3 months. Since then, rovers have become more advanced and longer-lived. Spirit and Opportunity landed in 2004, with Opportunity operating for over 14 years, far beyond its planned 90-day mission. Curiosity landed in 2012 and is still active, exploring Gale Crater and studying the planet's geology and climate. Perseverance landed in 2021 and is searching for signs of ancient life, while collecting samples for a future return mission. These rovers are our eyes and hands on Mars, exploring the surface, drilling into rocks, analyzing soil, and sending back stunning images of the Martian landscape. They've discovered evidence of ancient water, organic molecules, and environments that may have been habitable billions of years ago. The rovers are slow, methodical explorers, but they've transformed our understanding of Mars, turning it from a distant red dot into a real, tangible world. The Cassini mission revealed the beauty of Saturn. Cassini orbited Saturn for 13 years, from 2004 to 2017, studying the planet, its rings, and its moons in incredible detail. It discovered new moons, observed storms and weather patterns, and captured stunning images of the rings. Cassini also carried the Huygens probe, which landed on Titan in 2005, sending back images of the surface and data about the atmosphere. One of Cassini's most important discoveries was the geysers on Enceladus, which revealed the presence of a subsurface ocean. At the end of its mission, Cassini was deliberately crashed into Saturn's atmosphere to avoid contaminating any of the moons. The mission was a triumph of exploration, revealing the complexity and beauty of the Saturn system, and it provided data that will be studied for decades to come. The Juno mission is studying Jupiter. Juno arrived at Jupiter in 2016 and has been orbiting the planet ever since, studying its atmosphere, magnetic field, and interior structure. Juno's orbit is highly elliptical, taking it close to the planet's poles and then far away, allowing it to study Jupiter from different angles. The mission has revealed stunning details about Jupiter's auroras, its deep atmosphere, and the structure of its magnetic field. Juno has also taken incredible images of the planet's swirling clouds, showing the beauty and complexity of the atmosphere. The mission has helped scientists understand how Jupiter formed and how it has evolved over billions of years. Juno continues to orbit Jupiter, sending back data and images, revealing the secrets of the largest planet in our solar system. New Horizons transformed our view of Pluto. Before New Horizons, Pluto was just a blurry dot, even in the best telescopes. When the spacecraft flew by in 2015, it revealed a world far more complex and beautiful than anyone expected. Pluto has a heart-shaped region of smooth ice called Sputnik Planitia, mountains made of water ice, and a thin, hazy atmosphere that extends high above the surface. The mission also studied Pluto's moons, including Charon, and revealed that the Pluto-Charon system is dynamic and interesting. After the Pluto flyby, New Horizons continued into the Kuiper Belt and flew by a small object called Arrokoth, revealing a contact binary that looks like a snowman. New Horizons is still operational, continuing to explore the outer reaches of the solar system, sending back data from the edge of the Sun's influence. The James Webb Space Telescope is observing the solar system. While it's primarily designed to study distant galaxies and exoplanets, the James Webb Space Telescope has also been used to observe objects in our solar system. It has captured stunning images of Jupiter, revealing details in its auroras and atmosphere. It has studied the atmospheres of Saturn's moons and observed distant objects in the Kuiper Belt. Webb's infrared capabilities allow it to see details that are invisible to other telescopes, revealing the complexity and beauty of the solar system in new ways. The telescope is a powerful tool for studying the solar system, and it will continue to provide new insights into the planets, moons, and other objects that orbit the Sun. Planetary defense is a real concern. There are thousands of asteroids that cross Earth's orbit, and while most are small and pose no threat, some are large enough to cause significant damage if they were to impact the planet. Scientists are actively tracking these near-Earth objects, cataloging their orbits, and assessing the risk. In 2022, NASA's DART mission successfully demonstrated a method for deflecting an asteroid by crashing a spacecraft into it, changing its orbit slightly. This was a test of planetary defense technology, and it showed that we have the ability to protect Earth from potential impacts. Planetary defense is about being prepared, understanding the risks, and having the tools to respond if necessary. It's a reminder that Earth is part of a dynamic solar system where objects are constantly moving and interacting, and where we need to be vigilant. The solar system is about 4.6 billion years old. It formed from a cloud of gas and dust that collapsed under its own gravity, creating the sun and the planets. The early solar system was chaotic, with planets forming, migrating, and colliding. Over time, the system settled into the configuration we see today, with rocky planets close to the sun and gas giants farther out. The solar system has changed over billions of years, and it will continue to change in the future. The sun will eventually expand into a red giant, engulfing the inner planets. Some of the outer planets and their moons may survive, but the solar system as we know it will be very different. For now, the solar system is stable, a family of worlds orbiting the sun, each with its own story, its own history, and its own future. The planets formed from a protoplanetary disk. This disk was made of gas and dust left over from the formation of the sun. Small particles stuck together, growing larger over time, eventually forming planetesimals, rocky or icy bodies that were the building blocks of planets. These planetesimals collided and merged, growing into planets over millions of years. The inner planets, being closer to the sun, were too hot for ice to condense, so they formed from rock and metal. The outer planets, where it was colder, were able to capture large amounts of gas, becoming gas giants. This process of accretion, driven by gravity and collisions, is how the planets formed, and it's a process that's still happening in other star systems throughout the galaxy. The Grand Tack hypothesis explains the solar system's structure. This hypothesis suggests that Jupiter formed farther from the sun, and then migrated inward before reversing course and moving back out. As Jupiter moved, it influenced the orbits of other planets and scattered material throughout the solar system. This migration may explain why Mars is so small, why the asteroid belt exists, and why the inner solar system has the configuration it does. The Grand Tack is still a hypothesis, but it's supported by computer simulations and observations of other planetary systems. It's a reminder that the solar system's history is complex and dynamic, shaped by the movements and interactions of the planets over billions of years. The late heavy bombardment was a period of intense impacts. About 4 billion years ago, the inner solar system experienced a spike in asteroid and comet impacts. This period, called the late heavy bombardment, may have been caused by the migration of the giant planets, which destabilized the orbits of objects in the outer solar system and sent them careening inward. The impacts scarred the surfaces of the inner planets and moons, and they may have delivered water and organic molecules to Earth. The late heavy bombardment shaped the early solar system, and it may have played a role in the emergence of life on Earth. It's a reminder that the solar system has a violent past, and that the planets we see today are the survivors of billions of years of chaos. Tidal forces shape moons and planets. Tidal forces are caused by the difference in gravitational pull across an object. The side of a moon facing a planet experiences a stronger pull than the side facing away, and this difference creates stress and strain. Over time, tidal forces can lock a moon's rotation to its orbit, as we see with Earth's moon. Tidal forces can also generate heat inside a moon or planet, as we see with Io and Europa. This heating can drive volcanic activity or keep subsurface oceans liquid. Tidal forces can also cause moons to slowly spiral inward or outward, changing their orbits over time. Tidal forces are a subtle but powerful influence in the solar system, shaping the orbits, rotation, and geology of moons and planets. Lagrange points are special locations in space. These are points where the gravitational forces of two large bodies, like the Sun and Earth, balance with the centrifugal force of an object orbiting with them. There are 5 Lagrange points in the Sun-Earth system, labeled L1 through L5. Objects at these points can remain in a relatively stable position with minimal fuel. Spacecraft have been placed at Lagrange points to observe the Sun, study space weather, and conduct astronomical observations. The James Webb Space Telescope orbits around the Sun-Earth L2 point, about 1 million miles from Earth, where it has a clear view of the universe. Lagrange points are useful for space missions, and they're also places where dust and asteroids can accumulate, forming clouds or clusters that orbit along with the planets. Resonances create patterns in the solar system. A resonance occurs when 2 orbiting bodies exert regular, periodic gravitational influence on each other, usually because their orbital periods are related by a simple ratio. For example, Neptune and Pluto are in a 3.2 resonance, meaning Pluto completes 2 orbits for every 3 that Neptune completes. This resonance keeps them from colliding, even though their orbits cross. Resonances can also create gaps, like the Kirkwood gaps in the asteroid belt, where resonances with Jupiter have cleared out asteroids. Resonances are a subtle but important force in the solar system, creating patterns, stability, and sometimes chaos in the orbits of planets, moons, and asteroids. Some moons are tidally locked to their planets. Tidal locking occurs when a moon's rotation period matches its orbital period, so the same side always faces the planet. Earth's moon is tidally locked, which is why we always see the same face from Earth. Many of the moons of Jupiter, Saturn, and other planets are also tidally locked. This happens because of tidal forces, which create a bulge in the moon that the planet pulls on. Over time, this slows the moon's rotation until it matches the orbital period. Tidal locking is common in the solar system, and it affects the geology, climate, and appearance of moons. Some tidally locked moons have one side that's constantly facing the planet, and one side that's always facing away, creating different environments on each side. Impact craters tell the history of a planet or moon. Craters are formed when asteroids or comets collide with a surface, and the number and size of craters can tell us how old a surface is and how active it has been. Heavily cratered surfaces, like those on Mercury, the Moon, and Callisto, are very old, with billions of years of impacts recorded. Surfaces with fewer craters, like those on Europa and Enceladus, are younger, because geological activity has erased the older craters. Some craters have rays, bright streaks of material ejected during the impact, and some have central peaks, mountains formed when the surface rebounded after the impact. Craters are like scars, recording the history of bombardment and change, and they help scientists understand the age and evolution of planetary surfaces. Volcanism is not limited to Earth. Volcanic activity occurs on several other worlds in the solar system. Io, as we've discussed, is the most volcanically active body, with hundreds of active volcanoes. Venus has thousands of volcanoes, though it's not clear how many are currently active. Mars has ancient volcanoes, including Olympus Mons, but they appear to be extinct. Earth's moon had volcanic activity in the past, which created the dark plains called Maria. Some moons, like Enceladus and Triton, have cryovolcanism, where water, ammonia, or methane erupt instead of molten rock. Volcanism is a sign of geological activity, of heat and motion inside a world, and it shapes the surfaces and atmospheres of planets and moons. Plate tectonics may be unique to Earth. Plate tectonics is the process by which Earth's crust is divided into plates that move, collide, and slide past each other. This process creates mountains, earthquakes, and volcanic activity, and it recycles material between the surface and the interior. Earth is the only planet in the solar system known to have active plate tectonics, though some moons, like Europa, may have similar processes in their icy shells. Plate tectonics is important for regulating Earth's climate, recycling carbon, and creating diverse environments. It's one of the factors that makes Earth habitable, and it's a process that may be rare in the solar system, and perhaps even in the galaxy. Water ice exists throughout the solar system. While liquid water is rare, water ice is common. The polar ice caps of Mars are made of water ice and carbon dioxide ice. The rings of Saturn are mostly water ice. Many moons, including Europa, Enceladus, and Ganymede, have thick shells of water ice. Even asteroids and comets contain water ice. Water is one of the most common molecules in the universe, and in the cold outer solar system, it freezes into ice, shaping the surfaces and structures of countless worlds. The presence of water ice is important for understanding the potential for life, because liquid water is essential for life as we know it, and ice can melt or sublimate under the right conditions. Some planets and moons have subsurface oceans. Beneath the icy shells of several moons, there may be vast oceans of liquid water. Europa, Enceladus, Ganymede, and possibly Callisto and Titan all show evidence of subsurface oceans. These oceans are kept liquid by tidal heating, residual heat from formation, or radioactive decay. They may be in contact with rocky cores, where chemical reactions could provide energy for life. Subsurface oceans are some of the most promising places to search for life in the solar system, because they provide liquid water, energy, and possibly the right chemistry for life to emerge. These oceans are hidden deep beneath the ice, but they may be teeming with possibilities. Methane lakes exist on Titan. Titan is the only place in the solar system besides Earth with stable liquid on its surface. But instead of water, the lakes and seas are made of liquid methane and ethane. These hydrocarbons remain liquid at Titan's extremely cold temperatures, around -290 degrees Fahrenheit. The largest sea, Kraken Mare, is larger than the Caspian Sea on Earth. Titan's lakes are fed by methane rain, which falls from the thick atmosphere and carves channels and rivers on the surface. The Cassini mission studied these lakes and found that they vary in depth and composition. Titan's methane cycle is similar to Earth's water cycle, with evaporation, precipitation, and flow, creating a dynamic, ever-changing landscape. It's a strange, alien world, but in some ways, it mirrors Earth. Geysers on Enceladus shoot water into space. These geysers erupt from cracks near the moon's south pole, shooting water vapor, ice particles, and organic molecules hundreds of miles into space. The geysers are powered by a subsurface ocean, warmed by tidal heating, and they create a faint ring around Saturn as some of the material escapes into orbit. The Cassini spacecraft flew through the geyser plumes, analyzing the composition, and found salts and organic molecules, suggesting that the ocean beneath the ice may have the right conditions for life. The geysers are visible in images, plumes of ice glowing in the sunlight, a dramatic sign of activity on a small, distant moon. Enceladus is one of the most exciting places in the solar system, a little world with a big secret. Olympus Mons is the tallest volcano in the solar system. Located on Mars, Olympus Mons stands about 13.6 miles high, nearly 3 times the height of Mount Everest. It's a shield volcano formed by slow, steady eruptions of lava that built up over millions of years. The base of Olympus Mons is about 370 miles across, roughly the size of the state of Arizona. The volcano is so large that if you stood at the base, you wouldn't be able to see the summit because it would be beyond the horizon. The slopes are gentle, rising gradually over the vast distance. Olympus Mons is likely extinct with no recent eruptions, but it stands as a testament to the volcanic history of Mars, a giant frozen in time, towering over the Martian plains. Valles Marineris is the largest canyon in the solar system. Also on Mars, this massive canyon system stretches over 2,500 miles long, up to 120 miles wide, and reaches depths of up to 4 miles. It's so large that it would span the entire width of the United States if placed on Earth. Valles Marineris may have formed from tectonic activity, fractures in the crust as the planet cooled and contracted. Some parts of the canyon show signs of ancient water flow, suggesting that water may have carved or widened some of the channels. The canyon is a dramatic feature, visible even from space, a scar on the surface of Mars that reveals the planet's dynamic geological past. The hexagon on Saturn's North Pole is a unique feature. This is a 6-sided jet stream, a persistent weather pattern that surrounds Saturn's North Pole. Each side of the hexagon is about 8,600 miles long, wider than the diameter of Earth. The hexagon was discovered by the Voyager missions in the 1980s, and it has remained stable for decades. The cause of the hexagon is still not fully understood, but it's thought to be related to the planet's rotation and the dynamics of the atmosphere. Inside the hexagon, there's a massive storm at the North Pole, similar to a hurricane, with a well-defined eye. The hexagon is one of the strangest and most beautiful features in the solar system, a geometric pattern in the swirling clouds of a gas giant. Jupiter's auroras are the most powerful in the solar system. They're caused by charged particles from the solar wind and from Jupiter's moons, particularly Io, interacting with the planet's magnetic field. The auroras on Jupiter are far more intense than those on Earth, glowing brightly in ultraviolet and infrared light. They're constantly active, creating rings of light around the poles that can be hundreds of times more energetic than Earth's auroras. Jupiter's auroras are influenced by the volcanic activity on Io, which supplies charged particles that get caught in Jupiter's magnetic field and spiral down to the poles. These auroras are a sign of the complex interactions between Jupiter, its moons, and the space around it, a beautiful display of energy and motion. Saturn's moon Mimas looks like the Death Star. Mimas has a large impact crater called Herschel, which is about 1/3 the diameter of the Moon. The crater gives Mimas a striking resemblance to the Death Star from Star Wars. The impact that created Herschel was so powerful that it nearly shattered the Moon. If the impactor had been slightly larger or hit with more energy, Mimas might have been destroyed entirely. Instead, the Moon survived, and the crater remains as a dramatic feature on its surface. Mimas is a small, icy moon and is heavily cratered, a reminder of the violence of the early solar system. The resemblance to the Death Star is purely coincidental, but it's made Mimas one of the most recognizable moons in the solar system. Iapetus has a two-toned appearance. One hemisphere of this moon of Saturn is bright and icy, while the other is dark and covered in a reddish-brown material. The contrast is stark, making Iapetus look like a yin-yang symbol. The dark material may come from dust or debris from other moons, or it may be material that darkens when exposed to sunlight. Iapetus also has a unique equatorial ridge that runs along much of its equator, making it look like a walnut. The ridge is several miles high and spans thousands of miles. The origin of the ridge is unknown, but it may be the result of ancient tectonic activity or the remnants of a collapsed ring system. Iapetus is one of the strangest moons in the solar system, with features that still puzzle scientists. Hyperion is a chaotic, sponge-like moon. It's one of Saturn's moons, and it has an irregular shape and a heavily cratered surface that looks like a sponge. Hyperion's rotation is chaotic, meaning it tumbles unpredictably as it orbits Saturn. This is unusual for a moon, and is likely due to its irregular shape and the gravitational influences of other moons. Hyperion's surface is covered in deep craters with sharp edges, giving it a unique texture. The moon is mostly ice, and it has a very low density, suggesting it's porous and filled with voids. Hyperion is a strange, tumbling world, a relic of the early solar system with a surface unlike any other. Miranda has a patchwork surface. This moon of Uranus has one of the most unusual surfaces in the solar system, with regions that look completely different from each other. Some areas are heavily cratered and ancient, while others are covered in grooves, ridges, and cliffs. The tallest cliff on Miranda, Verona Rupes, is about 12 miles high, the tallest known cliff in the solar system. The patchwork appearance may be the result of tidal heating in the past, which caused the moon to partially melt and resurface. Another theory is that Miranda was shattered by a massive impact and then reassembled, with pieces coming together in a jumbled configuration. Whatever the cause, Miranda's surface is chaotic and fascinating. A small moon with a big story. Ariel has the brightest surface of Uranus's moons. This moon has a relatively young surface, with fewer craters than the other moons, suggesting that it has been resurfaced by geological activity. Ariel has valleys, ridges, and bright deposits that may be frost or ice. The moon's surface is covered in a mix of water ice and rock, and it's one of the most reflective moons of Uranus. Ariel's surface suggests that it was geologically active in the past, possibly due to tidal heating, though it appears to be quiet now. It's a bright, icy world circling Uranus in the distant outer solar system. Triton orbits Neptune backwards. This retrograde orbit, combined with Triton's size and composition, strongly suggests that it's a captured Kuiper Belt object. Triton is the seventh largest moon in the solar system, and it's the only large moon with a retrograde orbit. This makes it unique and interesting, and it raises questions about how it was captured and what its history has been. Triton's surface is young and active, with geysers and a thin atmosphere. The moon's orbit is slowly decaying, and in the future, it will be torn apart by tidal forces, creating a spectacular ring system around Neptune. Triton is a captured world, a visitor from the outer solar system now bound to Neptune. Nereid has one of the most eccentric orbits of any moon. This moon of Neptune has an orbit that takes it from about 850,000 miles from Neptune at its closest to about 5.9 million miles at its farthest. This extreme eccentricity suggests that Nereid may have been perturbed by the capture of Triton, which disrupted the orbits of Neptune's other moons. Nereid is small and irregularly shaped, and it may be a captured object or a fragment of a larger body. Its orbit is unusual and unstable, making it one of the more interesting moons in Neptune's system. Phobos is slowly spiraling into Mars. This small moon orbits very close to Mars, and tidal forces are causing it to lose altitude. In about 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces, creating a temporary ring around the planet. Phobos is covered in craters and grooves, and it may be a captured asteroid. The grooves may have been caused by the impact that created the large Stickney crater, or they may be stress fractures from the tidal forces. Phobos is a small, doomed moon, slowly falling toward Mars. Deimos is the smaller of Mars's two moons. It orbits farther from Mars than Phobos, and it's moving slowly away from the planet. Deimos is also irregularly shaped and heavily cratered, and it may be a captured asteroid. From the surface of Mars, Deimos would appear as a bright star, much smaller and dimmer than Phobos. The two moons are named after the sons of Ares, the Greek god of war, fitting companions for the red planet. The frost line in the early solar system determined what could form where. The frost line, also called the snow line, is the distance from the sun where temperatures are low enough for volatile compounds like water, ammonia, and methane to condense into solid ice. Inside the frost line, it was too hot for ice to form, so the planets that formed there, like Earth and Mars, are rocky. Outside the frost line, ice could condense, and the planets that formed there, like Jupiter and Saturn, were able to capture large amounts of gas, becoming gas giants. The frost line played a crucial role in determining the composition and structure of the planets, and it's one of the reasons why the inner and outer solar system look so different. Differentiation shaped the interiors of planets. Differentiation is the process by which a planet or moon separates into layers based on density. When a body is molten or partially molten, heavier materials like iron sink to the center, forming a core, while lighter materials rise to form a mantle and crust. Earth, for example, has an iron core, a rocky mantle, and a thin crust. Differentiation requires heat, which can come from the energy of impacts, radioactive decay, or gravitational compression. Not all bodies are differentiated. Some asteroids and small moons are undifferentiated, meaning their interiors are relatively uniform. Differentiation is an important process in planetary formation, and it shapes the structure and geology of planets and moons. Accretion built the planets. Accretion is the process by which small particles stick together and grow into larger bodies. In the early solar system, dust grains collided and stuck together, forming larger clumps. These clumps grew into planetesimals, rocky or icy bodies that were the building blocks of planets. Planetesimals collided and merged, growing into planets over millions of years. Accretion is driven by gravity and collisions, and it's a slow, gradual process. Some planets, like the gas giants, grew large enough to capture gas from the surrounding disk, while others, like the rocky planets, formed from solid material. Accretion is the fundamental process of planet formation, and it's happening in protoplanetary disks around other stars throughout the galaxy. The nebular hypothesis explains how the solar system formed. This hypothesis, first proposed in the 18th century, suggests that the solar system formed from a rotating cloud of gas and dust called the solar nebula. As the cloud collapsed under its own gravity, it began to spin faster, flattening into a disk. The center of the disk became dense and hot, eventually forming the sun. The material in the disk began to clump together, forming planetesimals and eventually planets. The nebular hypothesis explains many features of the solar system, including why the planets orbit in the same direction and in the same plane, and why the sun contains most of the mass. It's the leading explanation for how the solar system formed, and it's supported by observations of protoplanetary disks around other stars. The moon formed from a giant impact. The leading theory for the moon's formation is the giant impact hypothesis, which suggests that a Mars-sized object collided with the early Earth, ejecting debris into orbit. This debris eventually coalesced into the moon. This hypothesis explains several features of the moon, including its size, composition, and orbit. The impact would have been incredibly violent, melting much of Earth's surface and vaporizing large amounts of material. The debris that formed the moon would have been a mix of material from both Earth and the impactor. Over time, the debris cooled and solidified, forming the moon we see today. The giant impact hypothesis is supported by computer simulations and by the similarity between the composition of Earth and the moon. Pluto's heart is made of nitrogen ice. The heart-shaped region on Pluto, called Sputnik Planitia, is a smooth plain of frozen nitrogen, carbon monoxide, and methane. The plain is relatively young with very few craters, suggesting that it's been resurfaced recently by geological activity. The nitrogen ice is thought to slowly flow, like a glacier, creating the smooth surface. Sputnik Planitia may be located in a large impact basin, and the ice may have accumulated there over time. The heart is one of the most distinctive features on Pluto, and it's a sign that the dwarf planet is more active and dynamic than anyone expected. Kuiper Belt objects are remnants of planet formation. The Kuiper Belt is filled with icy bodies that never formed into a planet. They're leftover building blocks, scattered and frozen, orbiting in the distant outer solar system. Studying these objects helps scientists understand the composition and conditions of the early solar system. Some Kuiper Belt objects, like Pluto, Haumea, and Makemake, are large enough to be classified as dwarf planets. Others are smaller, irregularly shaped chunks of ice and rock. The Kuiper Belt is a time capsule, preserving material from the solar system's formation, and it's a frontier for exploration. Haumea is a rapidly spinning dwarf planet. It rotates once every 4 hours, which is incredibly fast for an object of its size. The rapid rotation has distorted Haumea's shape, stretching it into an elongated football-like form. Haumea has 2 small moons and a ring system, making it one of the most unusual objects in the Kuiper Belt. The ring may have formed from debris knocked off the surface by an impact. Haumea's surface is covered in water ice, and it's one of the brightest objects in the Kuiper Belt. It's a strange, fast-spinning world, tumbling through the outer solar system. Makemake is another large Kuiper Belt object. It's about 2/3 the size of Pluto and has a reddish surface, likely due to the presence of frozen methane and other organic compounds. Makemake has at least 1 small moon, and it's one of the largest known objects in the Kuiper Belt. Studying Makemake helps scientists understand the diversity of objects in this distant region and the processes that shape them. Eris is slightly smaller than Pluto, but more massive. Eris is a dwarf planet located in the scattered disk, a region beyond the Kuiper Belt. It's one of the most distant known objects in the solar system, and its discovery in 2005 was one of the factors that led to Pluto being reclassified as a dwarf planet. Eris is very reflective, with a surface covered in methane ice. It has one known moon, Dysnomia. Eris's orbit is highly elliptical and tilted, taking it from about 38 astronomical units from the Sun at its closest to about 98 astronomical units at its farthest. Eris is cold, distant, and mysterious, one of the icy worlds at the edge of the solar system. Sedna has one of the longest orbital periods. Sedna is a distant object with an extremely elongated orbit. It takes about 11,400 years to complete one orbit around the Sun. At its closest, Sedna is about 76 astronomical units from the Sun, but at its farthest, it's about 937 astronomical units away. Sedna's orbit is so distant that it's barely influenced by the Sun's gravity, and some scientists have suggested that it may have been perturbed by a passing star in the distant past. Sedna is reddish in color, and it's one of the most distant objects known in the solar system. Its orbit raises questions about the outer reaches of the solar system and what else might be out there. The hypothetical Planet 9 may exist. Some astronomers have proposed that there may be a large planet, perhaps 5 to 10 times the mass of Earth, orbiting in the distant outer solar system. This planet, often called Planet 9, has not been directly observed, but its existence has been inferred from the unusual orbits of some distant Kuiper Belt objects, which seem to be clustered in a way that suggests they're being influenced by a large, unseen object. If Planet 9 exists, it would be very far from the Sun, perhaps 400 to 800 astronomical units away, and it would take tens of thousands of years to complete one orbit. The search for Planet 9 is ongoing, and if it's found, it would be a major discovery, adding a new member to the family of planets. Solar eclipses occur when the moon passes between Earth and the Sun. During a total solar eclipse, the moon completely covers the Sun, and the sky darkens as if it were night. The Sun's corona, its outer atmosphere, becomes visible as a faint glowing halo around the moon. Solar eclipses are rare events, and they can only be seen from specific locations on Earth. The path of totality, the area where the eclipse is total, is usually only a few hundred miles wide. Outside of this path, the eclipse is partial, with only part of the Sun covered. Solar eclipses are beautiful, awe-inspiring events, and they've been observed and recorded by humans for thousands of years. Lunar eclipses occur when Earth passes between the Sun and the Moon. During a lunar eclipse, Earth's shadow falls on the Moon, darkening it. Lunar eclipses can be total or partial, depending on how much of the Moon passes through Earth's shadow. During a total lunar eclipse, the Moon doesn't disappear completely. Instead, it takes on a reddish color, often called a blood moon. This happens because some sunlight passes through Earth's atmosphere and is bent, or refracted, onto the Moon. The atmosphere filters out blue light, leaving the red light to illuminate the Moon. Lunar eclipses are visible from anywhere on the night side of Earth, making them more widely observed than solar eclipses. Transits occur when a planet passes between Earth and the Sun. From our perspective, the planet appears as a small black dot moving across the face of the Sun. Transits of Mercury and Venus are rare, with Mercury transiting about 13 times per century, and Venus transiting only about twice per century. Transits were historically important for calculating the distance to the Sun and the size of the solar system. Today, transits are still observed by astronomers, and the technique of watching for transits has been used to discover thousands of exoplanets. When a planet passes in front of its star, it causes a tiny dip in the star's brightness, and by measuring that dip, astronomers can learn about the planet's size, orbit, and sometimes even its atmosphere. Oppositions occur when Earth passes between the Sun and an outer planet. During opposition, the planet is at its closest to Earth and appears brightest in the sky. It rises at sunset, is visible all night, and sets at sunrise. Oppositions are the best time to observe outer planets like Mars, Jupiter, and Saturn. Mars, in particular, can vary greatly in brightness and size depending on whether it's near opposition or on the opposite side of the Sun. During a close opposition, Mars can appear very bright and large through a telescope, revealing details on its surface. Conjunctions occur when two planets appear close together in the sky. While the planets are actually millions of miles apart, from our perspective on Earth, they can appear to pass very close to each other. Great conjunctions of Jupiter and Saturn occur about every 20 years, and they're among the most striking alignments. Planetary conjunctions have been observed and recorded for thousands of years, and they were often seen as omens or significant events. Today, they're beautiful events to observe, reminders of the motion and alignment of the planets in their orbits. Retrograde motion is an apparent reversal of a planet's motion. From Earth, outer planets like Mars, Jupiter, and Saturn sometimes appear to move backwards in the sky. This is an optical illusion caused by the relative motion of Earth and the other planet as they orbit the Sun. When Earth overtakes an outer planet in its orbit, the planet appears to move backwards against the background stars. After a while, the planet resumes its normal motion. Retrograde motion puzzled ancient astronomers, but it was eventually explained by the heliocentric model of the solar system, which places the Sun at the center. Retrograde motion is a reminder that our view of the solar system is from a moving platform, and that the motion of the planets is complex and beautiful. The zodiac is a band of constellations along the ecliptic. The ecliptic is the path the Sun appears to follow across the sky over the course of a year, and it's also the plane in which the planets orbit. The zodiac consists of 12 constellations that lie along this path, and the Sun, Moon, and planets appear to move through these constellations as they orbit. The zodiac has been used for thousands of years in astrology and astronomy, and it's a way of dividing the sky into sections. While astrology has no scientific basis, the zodiac constellations are still used by astronomers as reference points for locating objects in the sky. Precession causes the slow wobble of Earth's axis. Earth's axis is tilted at about 23.5 degrees, and this tilt causes the seasons. But the axis also wobbles slowly, like a spinning top that's winding down. This wobble, called precession, takes about 26,000 years to complete one cycle. Precession changes which star is the North Star over time. Currently, Polaris is the North Star, but in about 13,000 years, Vega will be closer to the North Celestial Pole. Precession also shifts the timing of the seasons relative to Earth's orbit, though the effect is very gradual. precession is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge, and it's a slow, steady motion that affects the way we see the stars. The solar system is moving through the galaxy. The Sun, along with all the planets, moons, and other objects, is orbiting the center of the Milky Way galaxy. It takes about 225 to 250 million years to complete one orbit, a period sometimes called a galactic year. The solar system is also moving relative to nearby stars, traveling through space at about 500,000 miles per hour. This motion is part of the galaxy's rotation, and it means that the solar system is constantly passing through different regions of the galaxy, encountering different densities of gas, dust, and stars. The solar system's motion through the galaxy is slow and steady, a journey that has been ongoing for billions of years. The Sun will eventually become a red giant. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing helium. As it does, it will expand, growing hundreds of times larger than it is now. The Sun will become a red giant, and its outer layers will extend beyond the orbit of Mercury and possibly Venus. Earth will be scorched, its oceans boiled away, its atmosphere stripped. Eventually, the Sun will shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf. The white dwarf will slowly cool over billions of years, eventually fading to a black dwarf. The Sun's transformation will mark the end of the solar system as we know it, but it's a natural part of stellar evolution, a process that all stars like the Sun will undergo. Planetary nebulae are shells of gas ejected by dying stars. When a star like the Sun reaches the end of its life, it sheds its outer layers, creating a glowing cloud of gas that expands into space. This cloud is called a planetary nebula, though it has nothing to do with planets. The name comes from early astronomers who thought these objects looked like planets through their telescopes. Planetary nebulae are beautiful, with intricate shapes and colors caused by different elements glowing at different wavelengths. The central star, now a white dwarf, illuminates the gas, causing it to glow. Over time, the nebula expands and fades, eventually dispersing into the interstellar medium. Planetary nebulae are one of the ways that stars return material to space, enriching the galaxy with the elements created during the star's life. White dwarfs are the remnants of stars like the Sun. After a star sheds its outer layers and becomes a planetary nebula, the core that's left behind is a white dwarf. White dwarfs are incredibly dense, with a mass similar to the Sun's but a size similar to Earth's. They're so dense that a teaspoon of white dwarf material would weigh several tons. White dwarfs are very hot when they first form, but they have no source of energy, so they slowly cool over billions of years. Eventually, they fade to black dwarfs, cold, dark remnants that no longer emit light. White dwarfs are the final stage of evolution for stars like the Sun, and they're common in the galaxy, though most are too faint to see without a telescope. The interstellar medium is the gas and dust between the stars. It's mostly hydrogen and helium, with traces of heavier elements. The interstellar medium is very diffuse, with densities far lower than the best vacuum we can create on Earth. But it's the material from which stars and planets form. Over time, regions of the interstellar medium can collapse under gravity, forming new stars. The interstellar medium is enriched by material from dying stars, including elements created in supernova explosions. This recycling of material is how the galaxy evolves, with each generation of stars contributing to the next. The solar system formed from the interstellar medium billions of years ago, and one day, the Sun will return its material to the interstellar medium, continuing the cycle. Dust grains in space are the seeds of planets. These tiny particles, smaller than a grain of sand, are made of silicates, carbon, and ice. In the cold, dense regions of molecular clouds, dust grains stick together, growing into larger clumps. Over time, these clumps become pebbles, boulders, and eventually planetesimals. Dust grains are also important for cooling gas, allowing it to collapse and form stars. Without dust, the process of star and planet formation would be very different. Dust grains absorb and scatter light, creating dark clouds and nebulae that block our view of distant stars. They're tiny, but they play a crucial role in the formation of stars, planets, and the structure of the galaxy. The solar system is full of organic molecules. Organic molecules are compounds containing carbon, and they're the building blocks of life. Organic molecules have been found in meteorites, comets, asteroids, and on the surfaces of planets and moons. They form in space through chemical reactions, often in the cold, dark regions of molecular clouds. Some organic molecules are simple, like methane and formaldehyde. Others are more complex, like amino acids and polycyclic aromatic hydrocarbons. The presence of organic molecules throughout the solar system suggests that the ingredients for life are common and widespread. This raises the possibility that life could emerge in many places, not just on Earth, but on other worlds where the right conditions exist. The search for life in the solar system is ongoing. Scientists are looking for signs of life, past or present, on Mars, Europa, Enceladus, and Titan. Rovers on Mars are searching for evidence of ancient life, studying rocks and soil for organic molecules and signs of past water. Future missions may drill into the ice of Europa or Enceladus, searching for life in their subsurface oceans. Titan's complex chemistry makes it another target, though life there would be very different from life on Earth. The search for life is one of the most exciting frontiers in planetary science, and every new discovery brings us closer to answering the question, are we alone? Astrobiology is a study of life in the universe. It combines biology, chemistry, geology, and astronomy to understand how life begins, how it evolves, and where it might exist. Astrobiologists study extremophiles, organisms on Earth that live in extreme environments, to understand the limits of life. They also study the conditions on other planets and moons, looking for places where life might be possible. Astrobiology is a multidisciplinary field, and it's expanding our understanding of what life is and where it can exist. The solar system is a natural laboratory for astrobiology, with diverse environments and the potential for life in unexpected places. The greenhouse effect warms planetary surfaces. The greenhouse effect occurs when an atmosphere traps heat, warming the surface of a planet. Sunlight passes through the atmosphere and heats the surface, and the surface radiates heat back into space. But some gases in the atmosphere, like carbon dioxide and water vapor, absorb this heat and re-radiate it back toward the surface, warming it further. Earth has a natural greenhouse effect that makes the planet habitable. Without it, Earth would be much colder. Venus has a runaway greenhouse effect, where the thick atmosphere traps so much heat that the surface is hot enough to melt lead. The greenhouse effect is important for understanding planetary climates and the potential for life. Ice ages have shaped Earth's history. Earth has experienced many ice ages, periods when temperatures drop and ice sheets expand across the continents. The most recent ice age ended about 11,700 years ago, and during its peak, ice covered much of North America, Europe, and Asia. Ice ages are caused by changes in Earth's orbit and axial tilt, which affect how much sunlight reaches different parts of the planet. These changes, called Milankovitch cycles, cause the climate to shift over tens of thousands of years. Ice ages have shaped the landscape, carving valleys and creating features like the Great Lakes. They've also influenced the evolution of life, including humans, who adapted to the changing climate. The carbon cycle regulates Earth's climate. Carbon moves between the atmosphere, oceans, land, and living organisms in a process called the carbon cycle. Plants absorb carbon dioxide from the atmosphere during photosynthesis, and animals release it through respiration. Carbon is also stored in rocks, soil, and fossil fuels. The carbon cycle helps regulate Earth's climate by controlling the amount of carbon dioxide in the atmosphere. When carbon dioxide levels rise, temperatures increase due to the greenhouse effect. When levels fall, temperatures drop. Human activities, like burning fossil fuels, are adding carbon dioxide to the atmosphere faster than the natural carbon cycle can remove it, leading to climate change. The ozone layer protects life on Earth. The ozone layer is a region of Earth's stratosphere that contains high concentrations of ozone, a molecule made of 3 oxygen atoms. Ozone absorbs harmful ultraviolet radiation from the sun, preventing it from reaching the surface. Without the ozone layer, life on land would be exposed to dangerous levels of UV radiation, which can cause skin cancer, cataracts, and damage to plants and animals. In the 1980s, scientists discovered that chemicals called chlorofluorocarbons were depleting the ozone layer, creating a hole over Antarctica. International agreements, like the Montreal Protocol, have helped reduce the use of these chemicals, and the ozone layer is slowly recovering. The ozone layer is a crucial part of Earth's atmosphere, protecting life from the sun's harmful rays. Earth's magnetic field protects us from the solar wind. The magnetic field is generated by the motion of molten iron in Earth's core, and it extends far into space, creating the magnetosphere. The magnetosphere deflects most of the charged particles from the solar wind, preventing them from stripping away the atmosphere. Mars lost much of its atmosphere because it lacks a strong magnetic field, and the solar wind eroded it over billions of years. Earth's magnetic field also creates the auroras, beautiful displays of light near the poles when charged particles interact with the atmosphere. The magnetic field is dynamic, and it has flipped many times in Earth's history, with the north and south magnetic poles switching places. The magnetic field is essential for life on Earth, protecting the atmosphere and shielding us from harmful radiation. The moon stabilizes Earth's axial tilt. Without the moon, Earth's axis would wobble much more dramatically, leading to extreme climate variations. The moon's gravity helps stabilize the tilt, keeping it relatively constant at about 23.5 degrees. This stability is important for maintaining a consistent climate over long periods, which has allowed life to evolve and thrive. The moon also creates tides. which may have played a role in the development of life by creating intertidal zones where organisms could adapt to changing conditions. The moon's influence on Earth is profound, affecting the climate, tides, and even the length of the day. The length of Earth's day is increasing. Tidal interactions between Earth and the Moon are gradually slowing Earth's rotation. The Moon's gravity pulls on Earth's oceans, creating tides, and the friction from these tides is slowing Earth's rotation by about 1.7 milliseconds per century. As Earth slows, the Moon is slowly moving away, drifting about 1.5 inches farther from Earth each year. Billions of years ago, the day was much shorter, and the Moon was much closer. Billions of years from now, the day will be longer, and the Moon will be farther away. This slow dance between Earth and the Moon is a reminder that the solar system is dynamic and ever-changing. Earth is the most geologically active rocky planet. Earth has active plate tectonics, volcanic eruptions, earthquakes, and a dynamic surface shaped by erosion and weathering. This geological activity is driven by heat from Earth's interior, which comes from radioactive decay and residual heat from the planet's formation. The activity recycles materials between the surface and the interior, creating new crust and shaping the landscape. Other rocky planets, like Mars and Mercury, were once active, but have since cooled and become geologically quiet. Venus may still have some volcanic activity, but it doesn't have plate tectonics like Earth. Earth's geological activity is one of the factors that makes it unique and habitable. The Goldilocks zone is a region where liquid water can exist, also called the habitable zone. This is the range of distances from a star where temperatures are right for liquid water to exist on a planet's surface. Earth is in the Sun's habitable zone, and so is Mars, though Mars is near the outer edge and is much colder. The habitable zone depends on the star's size and temperature. Smaller, cooler stars have habitable zones that are closer to the star, while larger, hotter stars have habitable zones that are farther away. The habitable zone is a useful concept for searching for life on other planets, though it's not the only factor that determines habitability. Atmosphere, geology, and many other factors also play a role. Water is essential for life as we know it. Water is a solvent, meaning it can dissolve many substances, which allows complex chemistry to occur. It's also a stable liquid over a wide range of temperatures, and it has unique properties like expanding when it freezes, which allows ice to float. These properties make water ideal for supporting life. On Earth, water is abundant, covering 71% of the surface. In the solar system, water is common in the form of ice, and there may be liquid water beneath the surfaces of several moons. The search for life often focuses on the search for water, because where there's water, there's the possibility of life. The atmosphere is essential for life on Earth. It provides oxygen for breathing, protects us from harmful radiation, and helps regulate temperature. The atmosphere is a thin layer of gas that surrounds Earth, held in place by gravity. It's made mostly of nitrogen and oxygen, with traces of other gases. The atmosphere creates weather, distributes heat around the planet, and allows sound to travel. Without the atmosphere, Earth would be a barren, lifeless rock, scorched by the sun during the day and frozen at night. The atmosphere is fragile, and it's important to protect it from pollution and damage. It's one of the things that makes Earth unique and habitable. Photosynthesis produces oxygen on Earth. Most of the oxygen in Earth's atmosphere is produced by plants, algae, and cyanobacteria through photosynthesis. These organisms use sunlight to convert carbon dioxide and water into glucose and oxygen. The oxygen is released into the atmosphere, where it's used by animals and other organisms for respiration. Photosynthesis is one of the most important processes on Earth, and it's the reason why the atmosphere contains oxygen. Billions of years ago, the atmosphere had very little oxygen, and photosynthesis by ancient cyanobacteria gradually increased the oxygen levels, leading to the oxygenation of the atmosphere. This event, called the Great Oxygenation Event, transformed Earth and allowed complex life to evolve. The solar system is a small part of the Milky Way galaxy. The Milky Way is a spiral galaxy containing hundreds of billions of stars, and the Sun is just one of them. The solar system is located in one of the spiral arms, about 26,000 light-years from the galactic center. The galaxy is vast, and the solar system is a tiny speck within it. The Milky Way is part of a larger group of galaxies called the Local Group, which includes the Andromeda Galaxy and several smaller galaxies. The universe is filled with billions of galaxies, each containing billions of stars. The solar system is a small, quiet corner of a vast, dynamic universe. We live in a dynamic, ever-changing solar system. The planets orbit, moons revolve, asteroids tumble, and comets streak through the darkness. The sun burns steadily, warming the planets and providing the energy for life. The solar system has a history shaped by collisions, migrations, and the slow passage of time. It has a future when the sun will transform and the planets will be reshaped or destroyed. But for now, the solar system is stable, a family of worlds circling a star, each with its own story, its own beauty, and its own mysteries. We are part of this system, inhabitants of a small blue planet, looking out at the other worlds and wondering what they're like. The solar system is our home, our neighborhood, and our first step into the cosmos. Comets have two types of tails. When a comet approaches the sun and begins to heat up, it develops two distinct tails. The dust tail is made of small particles of rock and dust that are pushed away from the comet by the pressure of sunlight. This tail is curved, following the comet's orbit, and it can be yellowish or white in color. The ion tail, also called the plasma tail, is made of ionized gas, charged particles that are blown away by the solar wind. This tail always points directly away from the sun, regardless of the comet's direction of motion, and it's usually blue in color due to the glow of ionized carbon monoxide. Some comets have very long tails that can stretch for millions of miles, while others have short, stubby tails. The tails are beautiful and ephemeral, appearing only when the comet is near the sun, and fading as it moves back into the cold outer solar system. Halley's Comet returns every 75 to 76 years. It's one of the most famous comets visible to the naked eye, and it's been recorded by astronomers for over 2,000 years. Halley's Comet last appeared in 1986 and will return in 2061. The comet follows a highly elliptical orbit that takes it from the outer solar system to within the orbit of Venus. When it's near the sun, it becomes bright and develops a long tail. Halley's Comet has been a source of wonder and sometimes fear throughout history, often seen as an omen. Today, we understand it as a natural phenomenon, a visitor from the outer solar system that returns regularly. The comet is named after Edmund Halley, who calculated its orbit and predicted its return, proving that comets follow predictable paths. Meteor showers occur when Earth passes through comet debris. As comets orbit the Sun, they leave behind trails of dust and small particles. When Earth's orbit intersects with one of these trails, the particles enter the atmosphere and burn up, creating meteors. Meteor showers occur at the same time each year because Earth passes through the same debris trails annually. The Perseids, which occur in August, are caused by debris from Comet Swift-Tuttle. The Leonids, in November, come from Comet Tempel-Tuttle. During a meteor shower, you can see dozens or even hundreds of meteors per hour, all appearing to radiate from a single point in the sky called the radiant. Meteor showers are beautiful, peaceful events, a reminder of the connection between comets and the Earth, and they're one of the easiest astronomical phenomena to observe. The Leonid meteor shower can produce meteor storms. In some years, when Earth passes through a particularly dense part of the debris trail, the Leonid meteor shower can produce thousands of meteors per hour, an event called a meteor storm. The most spectacular Leonid storms occurred in 1833 and 1966, when observers reported seeing meteors falling like snowflakes. These storms happen roughly every 33 years, when the parent comet, Tempel-Tuttle, returns to the inner solar system and refreshes the debris trail. Meteor storms are rare and unpredictable, but when they occur, they're spectacular, lighting up the night sky with thousands of streaks of light. Asteroids are classified by composition. There are three main types of asteroids, each with different compositions. C-type asteroids, or carbonaceous asteroids, are dark and rich in carbon. They're the most common type, making up about 75% of known asteroids. S-type asteroids, or silicaceous asteroids, are made of silicate rocks and metals. They're brighter and more reflective than C-type asteroids. M-type asteroids are metallic, made mostly of iron and nickel, and they may be the cores of larger bodies that were shattered by impacts. There are also other, rarer types, including V-type asteroids, which are thought to be fragments from the asteroid Vesta. Studying the composition of asteroids helps scientists understand the formation and evolution of the solar system. Vesta is one of the largest asteroids. It's about 326 miles in diameter, making it the second largest object in the asteroid belt after Ceres. Vesta has a differentiated interior, with a core, mantle, and crust, similar to the rocky planets. It's one of the few asteroids large enough to have undergone differentiation. Vesta has a giant impact crater near its south pole, called Rhea Silvia, which is about 310 miles across. The impact was so powerful that it ejected material into space, creating a family of smaller asteroids called Vestoids. The Dawn spacecraft orbited Vesta from 2011 to 2012, mapping its surface and studying its composition. Vesta is a fascinating object, a remnant from the early solar system that has survived largely intact. Some asteroids are contact binaries. These are asteroids that consist of two lobes touching each other, like a peanut or a rubber duck. Contact binaries likely formed when two separate asteroids collided gently and stuck together, or when a single asteroid was reshaped by rapid rotation. The asteroid Bennu, which was studied by the OSIRIS-REx mission, is thought to be a rubble pile, a collection of rocks and boulders loosely held together by gravity. Itokawa, studied by the Hayabusa mission, is also a rubble pile and has a distinctive peanut shape. These asteroids are fragile and loosely bound, and they provide clues about how asteroids evolve over time. Near Earth, Asteroids pass close to Earth. These are asteroids whose orbits bring them within 1.3 astronomical units of the Sun, which means they can come close to Earth. There are thousands of known near-Earth asteroids, and new ones are discovered regularly. Most are small and pose no threat, but a few are large enough that a collision would cause significant damage. Scientists track near-Earth asteroids carefully, cataloging their orbits and assessing the risk. The goal is to identify any potentially hazardous asteroids long before they pose a threat, giving us time to take action if necessary. Near-Earth asteroids are also interesting targets for exploration and possibly even mining, as they contain valuable materials and are relatively accessible. The Tunguska event was likely caused by an asteroid or comet. In 1908, a massive explosion occurred over a remote area of Siberia, flattening about 770 square miles of forest. The blast was so powerful that it was felt hundreds of miles away, and it's estimated to have been about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The cause is thought to have been a small asteroid or comet that exploded in the atmosphere before reaching the ground. No impact crater was found, which supports the idea that the object disintegrated in the air. The Tunguska event is a reminder that impacts are real and that even small objects can cause significant damage. The Chicxulub impact led to the extinction of the dinosaurs. About 66 million years ago, an asteroid about 6 miles in diameter struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact created a crater about 110 miles across and released energy equivalent to billions of atomic bombs. The impact threw vast amounts of dust and debris into the atmosphere, blocking out the sun and causing global temperatures to plummet. This led to the extinction of about 75% of all species on Earth, including the non-avian dinosaurs. The Chicxulub impact is one of the most significant events in Earth's history, and it shows the profound effect that asteroid impacts can have on life. Impact craters on Earth are eroded over time. Unlike the Moon and other bodies with no atmosphere, Earth has weather, water, and geological activity that erode and erase impact craters. Many ancient impact craters have been worn away or buried, making them difficult to find. Some of the most famous impact craters on Earth include Meteor Crater in Arizona, which is about 50,000 years old and well preserved, and the Vredefort Crater in South Africa, which is over 2 billion years old and one of the largest known impact structures. Studying impact craters helps scientists understand the history of impacts on Earth and the effects they've had on the planet and its life. The Moon's craters are ancient and well preserved, without an atmosphere or weather. The Moon's surface is unchanged by erosion. The craters we see today have been there for billions of years, a record of impacts from the early solar system. The largest craters, called basins, were created by massive impacts that melted the crust and created the dark plains we see from Earth. These plains, called Maria, were filled with lava that flowed from the Moon's interior billions of years ago. The Moon's craters are a window into the past, showing us what the early solar system was like when impacts were much more common. The far side of the Moon is different from the near side. The side of the Moon that faces away from Earth, often called the dark side, though it receives just as much sunlight, has a very different appearance. The far side has far fewer Maria, the dark plains of solidified lava, and is much more heavily cratered. The reason for this difference is still debated, but it may be related to the moon's formation and the thickness of the crust on each side. The far side was first photographed by the Soviet Luna 3 mission in 1959, and it wasn't until the Apollo missions and later lunar orbiters that we got detailed images of this hidden hemisphere. The far side is rugged, ancient, and mysterious. The moon is slowly drifting away from Earth. As we've mentioned, tidal interactions between Earth and the moon are causing the moon to move farther away at a rate of about 1.5 inches per year. Billions of years ago, the moon was much closer and the tides were much stronger. The day was also much shorter. Over time, the moon has been moving away, and Earth's rotation has been slowing. In the distant future, the moon will be so far away that it will no longer completely cover the sun during solar eclipses. The moon will appear smaller in the sky, and total solar eclipses will become impossible. The relationship between Earth and the moon is dynamic, constantly changing over time. The moon has no global magnetic field. Unlike Earth, the moon doesn't have a liquid core that generates a magnetic field. However, some rocks on the moon are magnetized, suggesting that the moon may have had a magnetic field in the past, possibly generated by a partially molten core. This magnetic field would have disappeared as the core cooled and solidified. The lack of a magnetic field today means the moon has no protection from the solar wind, and charged particles from the sun strike the surface directly. This affects the chemistry of the surface and creates a very thin, tenuous atmosphere called an exosphere. The moon's exosphere is incredibly thin. It's not really an atmosphere in the traditional sense, just a sparse collection of atoms and molecules. The exosphere contains helium, argon, neon, and other elements, but the density is so low that atoms rarely collide with each other. The exosphere is constantly being replenished by the solar wind, radioactive decay, and micrometeorite impacts that kick up atoms from the surface. It's also constantly being lost to space because the moon's gravity is too weak to hold on to the atoms for long. The moon's exosphere is a reminder of how different conditions are on airless worlds. Water ice exists in permanently shadowed craters on the moon. Near the moon's poles, there are craters that never receive sunlight. These permanently shadowed regions are some of the coldest places in the solar system, with temperatures as low as -400 degrees Fahrenheit. In these cold traps, water ice can exist for billions of years, protected from the sun's heat. Spacecraft missions have detected water ice in these craters, and future lunar missions may try to extract this ice for use as a resource. Water on the moon could be used for drinking, growing plants, or even split into hydrogen and oxygen for rocket fuel. The discovery of water ice on the moon has changed our understanding of the moon and has implications for future exploration. The Apollo missions brought back lunar samples. Between 1969 and 1972, 6 Apollo missions landed on the moon, and astronauts collected a total of about 842 pounds of lunar rocks and soil. These samples have been studied extensively, and they've provided invaluable information about the moon's composition, age, and history. The samples show that the moon is made of similar material to Earth, supporting the giant impact hypothesis. They also show that the moon was once geologically active, with volcanic eruptions that filled the Maria with lava. The Apollo samples are carefully preserved and continue to be studied by scientists around the world. Some samples have never been opened, saved for future generations with better technology. The moon has moonquakes. These are seismic events similar to earthquakes, caused by tidal stresses, impacts, and cooling of the moon's interior. Moonquakes are much weaker than earthquakes, but they can last for hours, with vibrations gradually fading away. The Apollo missions placed seismometers on the moon, and they detected thousands of moonquakes over several years. Studying moonquakes helps scientists understand the moon's interior structure and geological activity. Even though the moon appears quiet and inactive, it's still experiencing subtle changes and movements. The moon's surface is covered in regolith. Regolith is a layer of loose, fragmented material, including dust, soil, and broken rock that covers the moon's surface. It's created by billions of years of impacts, which shatter rocks and grind them into smaller and smaller pieces. The regolith is very fine, like talcum powder, and it clings to everything. During the Apollo missions, astronauts found that the dust stuck to their suits and equipment, and it was difficult to clean off. The regolith also contains tiny glass beads, created when impacts melt the surface and then cool rapidly. The regolith is a unique material, shaped by the harsh environment of space. The moon's gravity is about 1/6 of Earth's. This means that objects weigh much less on the moon than they do on Earth. An astronaut who weighs 180 pounds on Earth would weigh only 30 pounds on the moon. The lower gravity makes it easier to jump and move around, but it also affects how objects fall and behave. The Apollo astronauts demonstrated this by dropping a feather and a hammer at the same time, and both hit the ground simultaneously, because there's no air resistance on the moon. The lower gravity also means the moon can't hold on to a thick atmosphere, and it affects the way astronauts move, requiring a distinctive hopping gait. The moon influences Earth's tides. Tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun. The moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the moon and on the opposite side. As Earth rotates, different parts of the planet pass through these bulges, creating high and low tides. The sun also affects tides, and when the sun, Earth, and moon are aligned, during new moon and full moon, the tides are especially high, called spring tides. When the sun and moon are at right angles, during the quarter moons, the tides are lower, called neap tides. Tides affect coastal ecosystems, navigation, and even the rotation of Earth. The moon has been a source of inspiration throughout history. Cultures around the world have observed the moon, told stories about it, and used it to mark time. The phases of the moon were used to create calendars, and many ancient cultures tracked the lunar cycle. The moon appears in mythology, art, literature, and music. It's been seen as a goddess, a companion, a symbol of change and cycles. The moon's influence on human culture is profound, and it continues to inspire wonder and curiosity. The moon is a constant presence in our sky, a connection to the cosmos, and a reminder of the beauty of the universe. Mars has seasons similar to Earth. Mars's axial tilt is about 25 degrees, very close to Earth's 23.5 degrees, so it experiences seasons in a similar way. However, because Mars's orbit is more elliptical, the seasons are uneven in length. The southern hemisphere has shorter, more intense summers and longer, colder winters, while the northern hemisphere has longer, milder summers and shorter winters. During winter, carbon dioxide from the atmosphere freezes at the poles, forming seasonal ice caps. In summer, the ice sublimates, returning to the atmosphere. Dust storms can occur during the warmer months, sometimes growing to engulf the entire planet. Mars's seasons are dynamic and dramatic, shaping the planet's weather and surface. Mars once had liquid water on its surface. Evidence from rovers, orbiters, and landers shows that Mars had rivers, lakes, and possibly even an ocean billions of years ago. Ancient riverbeds, delta formations, and minerals that form in water have all been found on Mars. The planet's atmosphere was likely thicker in the past, warm enough to support liquid water. Over time, Mars lost much of its atmosphere, likely stripped away by the solar wind because Mars lacks a strong magnetic field. As the atmosphere thinned, temperatures dropped and water froze or evaporated. Today, Mars is cold and dry, but the evidence of its watery past is written in the rocks and landforms across the surface. Mars's soil contains perchlorates. These are chemical compounds that include chlorine and oxygen, and they're toxic to humans. The Phoenix lander and the Curiosity rover both detected perchlorates in the Martian soil. Perchlorates are a challenge for future human missions because they can be harmful if ingested or inhaled. However, they may also be useful, as they can be broken down to produce oxygen for breathing or rocket fuel. Understanding the chemistry of Mars's soil is important for planning future missions and for assessing the potential for life. Perchlorates can absorb water from the atmosphere, and they lower the freezing point of water, so liquid brines may exist in the soil under certain conditions. Mars has the largest dust storms in the solar system. These storms can grow to cover the entire planet, blocking out the sun and lasting for months. Dust storms on Mars are driven by temperature differences and winds, which can reach speeds of over 60 miles per hour. The dust is very fine, and it can be lifted high into the atmosphere, creating a global haze. During a global dust storm, temperatures can drop, and solar-powered spacecraft may lose power. The 2018 dust storm was so severe that it ended the Opportunity rover's mission after 14 years of operation. Dust storms are a major feature of Mars's climate, and they affect everything from weather patterns to the surface environment. Mars's atmosphere is mostly carbon dioxide. About 95% of the atmosphere is carbon dioxide, with small amounts of nitrogen and argon. The atmosphere is very thin, with a surface pressure less than 1% of Earth's. This thin atmosphere means that liquid water cannot exist on the surface, and temperatures vary widely. The atmosphere also provides very little protection from radiation, which is a concern for future human missions. Despite being thin, the atmosphere creates weather, including clouds, frost, and dust storms. The atmosphere of Mars is a key area of study, as it affects the climate, the potential for life, and the challenges of exploration. Curiosity rover has been exploring Mars since 2012. It landed in Gale Crater, a large impact crater that once held a lake. Curiosity is about the size of a car, and it's equipped with cameras, instruments, and a drill for studying rocks and soil. The rover has climbed Mount Sharp, a mountain in the center of the crater, studying the layers of rock to understand Mars's geological history. Curiosity has found evidence of ancient habitable environments, organic molecules, and methane in the atmosphere. The rover is nuclear-powered, which allows it to operate through the cold Martian nights and during dust storms. Curiosity continues to explore and send back data revealing the secrets of Mars. Perseverance rover is searching for signs of ancient life. It landed in Jezero Crater in 2021, a site that once held a river delta. Perseverance is similar to Curiosity, but has additional instruments designed to search for biosignatures, signs of past life. The rover is collecting rock samples and storing them in tubes, which will be retrieved and returned to Earth by a future mission. This sample return mission will allow scientists to study Martian rocks in detail in laboratories on Earth. Perseverance also carries a small helicopter called Ingenuity, which has demonstrated powered flight in Mars's thin atmosphere. The rover and helicopter are part of an ambitious effort to explore Mars and search for evidence of life. Ingenuity is the first aircraft to fly on another planet. This small helicopter, weighing only 4 pounds, made its first flight on Mars in 2021. Flying on Mars is challenging because the atmosphere is so thin, only about 1% the density of Earth's atmosphere. Ingenuity's blades spin much faster than a helicopter's on Earth to generate enough lift. The helicopter has made dozens of flights, scouting ahead of the Perseverance rover and demonstrating the potential for aerial exploration. Ingenuity has exceeded all expectations, continuing to fly long after its original planned mission. It's opened a new era of exploration, showing that aircraft can operate on other worlds. Mars has 2 very small moons. Phobos and Deimos are both small, irregularly shaped and heavily cratered. Phobos is the larger of the two, about 14 miles across, and it orbits very close to Mars. Deimos is smaller, about 7.5 miles across, and orbits farther out. Both moons are dark and rocky, and they may be captured asteroids. From the surface of Mars, Phobos would appear to rise in the west and set in the east, moving quickly across the sky. Deimos would move much more slowly and would appear as a bright star. The moons are fascinating objects, and future missions may study them more closely or even land on them. The Viking landers searched for life on Mars in the 1970s. Viking 1 and Viking 2 both landed on Mars in 1976, and they conducted experiments designed to detect signs of life in the soil. The results were ambiguous. Some tests gave positive results, but others did not, and the scientific consensus is that the positive results were likely caused by chemical reactions, not biological activity. The Viking missions were the first to search directly for life on another planet, and they paved the way for future missions. They also sent back the first images from the surface of Mars, showing a rocky, reddish landscape under a pink sky. Mars has ancient valley networks. These are branching channels that look like dried-up river systems, carved by flowing water billions of years ago. The valley networks are evidence that Mars once had a warmer, wetter climate. Some valleys are hundreds of miles long, and they show features like tributaries, meanders, and deltas. Studying these valleys helps scientists understand the history of water on Mars and the conditions that might have supported life. The valleys are ancient, dating back to the Noachian period over 3.7 billion years ago, when Mars was very different from the cold, dry planet we see today. Mars has gullies that may be active today. These are small channels on steep slopes, and some appear to be relatively young. For a while, scientists thought the gullies might be carved by liquid water flowing during warmer periods, but more recent studies suggest they may be formed by carbon dioxide frost or dry landslides. The exact mechanism is still debated, but the gullies are intriguing because they suggest that Mars's surface is still changing, even if slowly. Understanding how gullies form helps scientists learn about current processes on Mars and the potential for liquid water. Recurring slope lineae are dark streaks on Martian slopes. These streaks appear during warm seasons and fade during cold seasons, leading to speculation that they might be caused by briny water flowing down slopes. However, more recent studies suggest they may be caused by dry flows of sand and dust. The exact cause is still uncertain, but recurring slope lineae are an example of active processes on Mars. They show that the planet is not completely frozen and inactive, and they highlight the complexity of Martian surface processes. Mars's south polar ice cap is mostly water ice. The polar ice caps on Mars have two components, a permanent cap of water ice and a seasonal cap of carbon dioxide ice. During winter, carbon dioxide from the atmosphere freezes onto the poles, creating a thick layer of dry ice. In summer, this dry ice sublimates, returning to the atmosphere. The permanent cap beneath is water ice, mixed with dust. The South Polar Cap has layers that record the climate history of Mars, similar to ice cores on Earth. Studying the polar caps helps scientists understand Mars's climate and how it has changed over time. Jupiter's Great Red Spot is shrinking. Historical observations show that the storm was much larger in the 1800s, possibly large enough to fit 4 Earths inside. Today, it's about half that size, though still enormous. Scientists aren't sure why the storm is shrinking. It may be related to changes in Jupiter's atmosphere, or the dynamics of the storm itself. Despite shrinking, the Great Red Spot remains one of the most iconic features in the solar system, a massive storm that has raged for centuries. Observations from spacecraft like Juno are helping scientists understand the storm's structure and behavior. Jupiter has many smaller storms and features. In addition to the Great Red Spot, Jupiter has white ovals, brown barges, and other storms scattered across its atmosphere. Some of these storms last for decades, while others come and go more quickly. Jupiter's atmosphere is divided into bands of clouds that move at different speeds, creating turbulence and swirling patterns. The planet's rapid rotation drives powerful winds, creating a dynamic, ever-changing atmosphere. Observing Jupiter's atmosphere helps scientists understand atmospheric dynamics not just on Jupiter, but on other gas giants and even exoplanets. Jupiter emits more heat than it receives from the Sun. This is because Jupiter is still slowly contracting, releasing gravitational energy that was stored during its formation. This internal heat drives convection in the atmosphere, contributing to the planet's weather and storms. Jupiter is not quite massive enough to sustain nuclear fusion like a star, but it does generate its own heat, making it a warm, dynamic world. This heat affects the temperature of Jupiter's atmosphere and influences the behavior of its clouds and winds. Jupiter's magnetosphere is the largest structure in the solar system. It extends millions of miles into space, far beyond the planet itself. If we could see Jupiter's magnetosphere, it would appear larger than the full moon in Earth's sky, even though Jupiter is hundreds of millions of miles away. The magnetosphere is created by Jupiter's rapid rotation and its liquid metallic hydrogen interior, which generates a powerful magnetic field. The magnetosphere traps charged particles, creating intense radiation belts that are hazardous to spacecraft. It also interacts with Jupiter's moons, particularly Io, creating auroras and stripping material from the moon's surface. Io's volcanoes erupt constantly. Io has over 400 active volcanoes, making it the most volcanically active body in the solar system. The eruptions are driven by tidal heating, as Io is squeezed and stretched by the gravitational pull of Jupiter and the other Galilean moons. This constant flexing generates enormous heat inside Io, melting rock and driving volcanic activity. Some of Io's volcanoes erupt with plumes that shoot hundreds of miles into space. The surface of Io is constantly being resurfaced by lava flows, which is why there are no impact craters. Io is a world of fire, glowing faintly in the darkness of Jupiter's orbit. Io has a thin atmosphere of sulfur dioxide. This atmosphere is created by volcanic eruptions and sublimation of surface frost. The atmosphere is very thin, and it collapses and reforms depending on whether Io is in sunlight or in Jupiter's shadow. When Io passes into Jupiter's shadow, the temperature drops, and the sulfur dioxide freezes onto the surface. When Io emerges back into sunlight, the frost sublimates, creating the atmosphere again. Io's atmosphere is dynamic and tied directly to its volcanic activity and orbital position. Europa's surface is one of the smoothest in the solar system. There are very few craters, and the surface is covered in long cracks and ridges. The smoothness suggests that the surface is young, and that geological processes are actively reshaping it. The cracks may be caused by tidal forces that flex the ice shell, creating fractures. Some areas show evidence of cryovolcanism, where liquid water or slushy ice erupts onto the surface and then freezes. Europa's surface is a frozen shell covering a potentially habitable ocean, and understanding the surface helps scientists plan future missions to search for life. Europa's ocean may be in contact with a rocky seafloor. If this is true, then the ocean could have the right chemistry for life. On Earth, hydrothermal vents on the seafloor support rich ecosystems, with life thriving on chemical energy rather than sunlight. Europa's ocean may have similar vents, where water interacts with rock, creating chemical reactions that could support life. This makes Europa one of the most promising places to search for life in the solar system. Future missions may drill through the ice or search for plumes of water erupting from the surface, looking for signs of biology. Ganymede has a subsurface ocean beneath layers of ice. The ocean is sandwiched between two layers of ice, one near the surface and another, denser layer below the ocean. This structure is created by the high pressure deep inside Ganymede, which creates different forms of ice. Ganymede's ocean may contain more water than all of Earth's oceans combined, though it's hidden beneath miles of ice. The ocean is kept liquid by residual heat from Ganymede's formation, and possibly by tidal heating. Ganymede's complex interior makes it a fascinating target for study, a large moon with hidden depths. Callisto may have a subsurface ocean, but is less certain. Some data from the Galileo spacecraft suggests that Callisto may have a layer of liquid water deep beneath the surface, but the evidence is not as strong as it is for Europa or Ganymede. If Callisto does have an ocean, it's likely deep and isolated, with little interaction with the surface. Callisto's surface is ancient and heavily cratered, showing little sign of geological activity. It's a quiet, stable world, possibly with a hidden ocean, drifting through space around Jupiter. Jupiter's rings are faint and made of dust. Unlike Saturn's bright, icy rings, Jupiter's rings are dark and difficult to see. They're made of fine dust particles, likely created by micrometeorite impacts on Jupiter's small inner moons. The rings are tenuous and constantly being replenished as new dust is created. They were discovered by Voyager 1 in 1979, and they're best seen when backlit by the sun. Jupiter's rings are a reminder that ring systems can exist in many forms, not just the spectacular rings of Saturn. Saturn's rings are made mostly of water ice. The particles range in size from tiny grains to chunks as large as houses. The rings are incredibly thin, in some places only about 30 feet thick, but they extend over 175,000 miles from the planet. The rings are divided into several main sections, labeled A, B, C, D, E, F, and G, each with different characteristics. The B ring is the brightest and most massive, while the F ring is narrow and braided, shaped by the gravity of small moons. Saturn's rings are a beautiful, complex system, constantly changing and evolving. Saturn's rings have gaps and divisions. The most famous is the Cassini division, a large gap between the A and B rings. The gap is created by a resonance with the moon Mimas, which clears out particles at certain distances. There are also smaller gaps, some of which are caused by tiny moons orbiting within the rings, called shepherd moons. These moons sculpt the rings, creating gaps, waves, and braids. The rings are not solid structures, but dynamic systems, shaped by gravity, collisions, and the influence of Saturn's moons. Some of Saturn's moons orbit within the rings. These small moons, called moonlets, are embedded in the rings and help shape them. Pan and Daphnis are two examples, tiny moons that orbit in gaps within the rings. Their gravity creates waves and wakes in the ring particles, visible in images from the Cassini spacecraft. These moonlets are fascinating objects, small worlds that are intimately connected to the ring system, helping to maintain and shape the rings over time. Saturn's moon Titan has a thick, hazy atmosphere. The atmosphere is made mostly of nitrogen, similar to Earth's, but with significant amounts of methane and other hydrocarbons. The pressure at the surface is about 1.5 times that of Earth, and the atmosphere is so thick that it's opaque to visible light. The haze is created by complex organic chemistry in the upper atmosphere, where ultraviolet light from the sun breaks apart methane and triggers chemical reactions. The haze gives Titan its orange color and obscures the surface, making it difficult to see from space. The Huygens probe, which landed on Titan in 2005, descended through the haze and sent back images of the surface. Titan has lakes of liquid methane and ethane. These lakes are located mostly near the poles, and some of them are quite large. Kraken Mare, the largest, is bigger than the Caspian Sea. The lakes are fed by methane rain, which falls from the clouds and flows across the surface in rivers and streams. The liquid methane cycle on Titan is similar to Earth's water cycle, with evaporation, condensation, precipitation, and flow. Titan is the only other place in the solar system with stable liquid on its surface, making it a unique and fascinating world. Titan's surface has sand dunes made of hydrocarbon particles. These dunes are hundreds of feet tall and stretch for hundreds of miles, shaped by winds in Titan's thick atmosphere. The particles that make up the dunes are not sand in the traditional sense, but tiny grains of organic material, created by chemical reactions in the atmosphere. The dunes are located near Titan's equator, in regions that are relatively flat and dry. They're a striking feature of Titan's landscape, visible in radar images from the Cassini spacecraft. Titan may have cryovolcanoes. These would be volcanoes that erupt not with molten rock, but with water, ammonia, or methane. Evidence for cryovolcanism on Titan is tentative, but some features on the surface may be volcanic in origin. If Titan does have cryovolcanoes, they would be driven by internal heat, possibly from tidal heating or radioactive decay. Cryovolcanism would bring material from Titan's interior to the surface, potentially replenishing the methane in the atmosphere and affecting the surface chemistry. Enceladus is one of the brightest objects in the solar system. Its surface is covered in fresh, clean ice that reflects nearly all the sunlight that hits it. This makes Enceladus incredibly bright and beautiful, shining like a beacon in Saturn's orbit. The fresh ice comes from the geysers at the South Pole, which coat the surface with new snow. Enceladus is small, only about 300 miles across, but it's one of the most intriguing moons in the solar system, with active geology and the potential for life. The geysers on Enceladus were a major discovery. When the Cassini spacecraft first observed plumes of ice and water vapor erupting from Enceladus's south pole, it was a surprise. The discovery showed that this small moon is geologically active and has a subsurface ocean. The geysers erupt from cracks in the ice called tiger stripes, and they shoot material hundreds of miles into space. Some of the material falls back to the surface as snow, while the rest escapes and forms one of Saturn's faint outer rings, the E ring. The geysers are powered by tidal heating, and they provide a direct window into the ocean below. Enceladus's ocean contains organic molecules. When Cassini flew through the geyser plumes, it detected not just water vapor and ice, but also organic molecules, including methane, carbon dioxide, and more complex compounds. These molecules suggest that the ocean has the right chemistry for life, with carbon-based compounds and energy from hydrothermal vents on the ocean floor. Enceladus is now considered one of the best places in the solar system to search for life, and future missions may return to study the geysers and the ocean in more detail. Saturn's moon Mimas has a large crater that makes it look like the Death Star. The crater, called Herschel, is about 1/3 the diameter of the moon. The impact that created Herschel was so powerful that it nearly destroyed Mimas. Shock waves from the impact traveled through the moon, creating fractures and features on the opposite side. Mimas is a small, heavily cratered moon, and the resemblance to the Death Star is purely coincidental, but it's made Mimas famous and recognizable. Iapetus has a distinctive ridge along its equator. This ridge is several miles high and runs along much of the moon's equator, making Iapetus look like a walnut. The origin of the ridge is unknown, but it may be the result of ancient tectonic activity, the remnants of a collapsed ring system, or material that accumulated along the equator. Iapetus also has a two-toned appearance, with one hemisphere bright and icy, and the other dark and covered in a reddish-brown material. The dark material may come from dust or debris from other moons, or it may be material that darkens when exposed to sunlight. Hyperion is a chaotic, tumbling moon. Its rotation is not stable, and it tumbles unpredictably as it orbits Saturn. This is unusual for a moon, and is likely due to its irregular shape and the gravitational influences of other moons. Hyperion's surface is covered in deep craters with sharp edges, giving it a sponge-like texture. The moon is mostly ice, and it has a very low density, suggesting it's porous and filled with voids. Hyperion is a strange, tumbling world, a relic of the early solar system. Uranus was the first planet discovered with a telescope. It's barely visible to the naked eye, so it was unknown to ancient astronomers. William Herschel discovered Uranus in 1781, initially thinking it was a comet. After further observations, it was recognized as a new planet, the first planet discovered in modern times. The discovery of Uranus expanded the known solar system and showed that there were more worlds out there, waiting to be found. Uranus is named after the Greek god of the sky, the father of Saturn in mythology. Uranus's extreme axial tilt may be the result of a collision. The leading theory is that Uranus was hit by a large object, possibly an Earth-sized planet early in its history. The impact knocked Uranus onto its side, giving it the extreme tilt we see today. This collision may also have affected Uranus's moons and rings, tilting them along with the planet. The collision would have been catastrophic, but Uranus survived, and it's been rolling through space on its side ever since. Uranus's atmosphere is calm compared to Neptune. While Neptune has the fastest winds in the solar system, Uranus has a much more subdued atmosphere. There are some clouds and storms, but they're faint and difficult to see. Uranus's atmosphere is made mostly of hydrogen and helium, with methane giving it a blue-green color. The methane absorbs red light, reflecting blue and green light back into space. Uranus is cold and distant, receiving very little energy from the sun, which may explain why its atmosphere is so calm. Uranus has faint rings. They were discovered in 1977 when Uranus passed in front of a star, and the star's light blinked on and off several times before and after the planet passed in front of it. This indicated that Uranus had rings blocking the starlight. The rings are narrow, dark, and made of larger particles than Saturn's rings. There are 13 known rings, and they're all very faint and difficult to see. The rings may be the remnants of shattered moons, broken apart by impacts or tidal forces. Uranus's moons are named after characters from literature. Unlike most moons in the solar system, which are named after figures from Greek and Roman mythology, Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. This makes Uranus's moons unique, and it reflects the literary interests of the astronomers who discovered them. The largest moons are Titania, Oberon, Umbriel, Ariel, and Miranda, each with its own distinctive features and characteristics. Miranda has a patchwork surface. Some areas are heavily cratered and ancient, while others are covered in grooves, ridges, and cliffs. Verona Rupes, the tallest cliff on Miranda, is about 12 miles high, the tallest known cliff in the solar system. If you jumped off this cliff, you would fall for about 12 minutes before hitting the ground, due to Miranda's low gravity. The patchwork appearance may be the result of tidal heating in the past, or a massive impact that shattered the moon and then reassembled it. Miranda is a small moon with a dramatic, chaotic surface. Neptune is the windiest planet. Even though it's the farthest planet from the Sun and receives very little energy, Neptune has the fastest winds ever recorded on any planet, reaching speeds of over 1,200 miles per hour. These supersonic winds whip through the planet's atmosphere, creating massive storms and dark spots that come and go over time. The energy for these winds may come from Neptune's interior, as the planet emits more heat than it receives from the Sun. Neptune's atmosphere is dynamic and active, with features that change over days and weeks. Neptune has a dark spot similar to Jupiter's Great Red Spot. When Voyager 2 flew by Neptune in 1989, it observed a large dark storm in the southern hemisphere, called the Great Dark Spot. The storm was about the size of Earth and had winds of over 1,500 miles per hour. However, when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared. Other dark spots have appeared since then, showing that Neptune's atmosphere is constantly changing. These storms are anticyclones, similar to Jupiter's storms, but they're less stable and shorter-lived. Neptune's moon Triton orbits backwards. This retrograde orbit, combined with Triton's size and composition, strongly suggests that it's a captured Kuiper Belt object. Triton is the seventh largest moon in the solar system, and it's the only large moon with a retrograde orbit. This makes it unique and raises questions about how it was captured and what its history has been. Triton's orbit is slowly decaying, and in the future, it will be torn apart by tidal forces, creating a spectacular ring system around Neptune. Triton is geologically active, despite being one of the coldest places in the solar system, with surface temperatures around minus 390 degrees Fahrenheit. Triton has geysers that erupt nitrogen gas and dark material into the thin atmosphere. These geysers create dark streaks on the surface, visible in images taken by Voyager 2. The geysers are powered by sunlight, warming nitrogen ice beneath the surface, causing it to sublimate and erupt. Triton's surface is young and active, with few craters, showing that geological processes are reshaping the surface. Neptune's other moons are much smaller. Most of them orbit in irregular eccentric paths, and they may be captured objects or fragments of larger bodies. Nereid has one of the most eccentric orbits of any moon, taking it from very close to Neptune to very far away. Neptune's moons are diverse and interesting, but Triton is by far the largest and most intriguing, dominating the system with its size, activity, and unusual orbit. And now, our journey draws to a close. We've wandered through the solar system tonight, visiting every planet, exploring moons and rings, and drifting through fields of asteroids and comets. We've seen the scorching heat of Mercury, the thick clouds of Venus, the blue marble of Earth, and the red plains of Mars. We've marveled at the massive storms of Jupiter, the beautiful rings of Saturn, the tilted ice giants Uranus and Neptune, and the distant, frozen world of Pluto. We've explored moons with hidden oceans, active volcanoes, geysers erupting into space, and lakes of liquid methane. We've learned about impacts, tides, magnetic fields, and the slow dance of gravity that holds everything together. We've seen how dynamic and diverse the solar system is, full of motion, change, and beauty. Each world we've visited has its own story, its own history shaped by billions of years of formation, collision, and evolution. Some worlds are quiet and ancient, covered in craters and untouched by time. Others are active and dynamic, constantly reshaping themselves through volcanoes, weather, and geological forces. The solar system is our cosmic neighborhood, the family of worlds that orbit our sun. It's the only planetary system we can explore directly, the only place where we've sent spacecraft, landed rovers, and walked on another world. It's our home, our starting point, and our first step into the universe. As you rest here, comfortable and still, the planets continue their endless orbits. The sun shines steadily, Mars spins slowly beneath its dusty sky, and Saturn's rings glitter in the darkness. Jupiter's storms swirl, Neptune's winds howl, and Pluto drifts through the distant Kuiper belt, quietly turning in the cold. The solar system is vast, beautiful, and full of wonders. And though we've only begun to explore it, we've learned enough to know that it's a place of endless fascination, where every world has something to teach us, every moon has secrets to reveal, and every discovery reminds us how much more there is to learn. So if your eyes are heavy now, if your breath has settled into a gentle rhythm, if your thoughts have drifted like dust through the rings of Saturn, then rest. The solar system will continue, the planets will keep turning, and the wonders of space will wait for you, always there, always shining, always ready to welcome you back. Thank you for joining me on this peaceful journey through our solar system. And if you found this relaxing, if it helped you unwind and drift towards sleep, you're always welcome to return. There are always more worlds to visit, more moons to explore, more quiet facts to soothe you into rest. But for now, sleep well. The planets are still out there, circling in the dark, and they'll be there when you wake. Good night.